We have now examined both the Mercator and the Lambert's chart properties in some detail, and can see that the Lambert has both advantages and disadvantages. Looking at the positive side first, let's consider its advantages. The first is that great circles can be treated as straight lines for all practical purposes. As we said earlier, this is useful when flying with equipment that steers us on great circle tracks. Secondly, radio bearings are great circles, so they can be plotted without application of conversion angle. You still need to apply chart convergence in cases where the bearing is measured at the aircraft, but this can be achieved by plotting. No calculation is required. Finally, if scale error is small, a graduated ruler can be used to measure distances. So much for advantages. What about disadvantages? Great circle tracks are straight lines, so if we fly by compass, firstly we need to choose the track at mid-meridian, and secondly the aircraft will appear to wander off track and then back on again. On the other hand, if we wish to fly great circle tracks, the aircraft must be fitted with a system which provides automatic continuous computation of desired track. That is, INS, IRS, FMS or GPS. Not all aircraft are. The graticule is not rectangular, so the plotting of positions is not as straightforward as on a Mercator. And, as previously stated, you need to apply chart convergence in cases where the bearing is measured at the aircraft. We'll go on to the explanation of that now. Whether you need to apply a correction for chart convergence depends on whether the bearing is measured at the ground station or at the aircraft. The easier case is a bearing measured at the ground station. If you remember, the two navigational aids which operate on this principle are VDF and VOR. It is fairly self-evident that VDF is measured at the ground station, but it may not be quite so obvious that VOR is as well. You read the information in the aircraft, but the bearing signal was modulated at the ground station. Because, for all practical purposes, great circles appear as straight lines on Lambert's charts, there is no need to apply conversion angle. However, as with the Mercator, we are going to have to put our protractor over the ground station. We cannot plot from the aircraft because we don't know where it is. This is why we are navigating. When the bearing is measured at the ground station, there is no problem. We will have to apply variation if the bearing is magnetic and we wish to plot in true. But once that correction has been done, we simply put our protractor over the ground station and plot the bearing. The line represents the correct radio path. However, there may be a problem if the bearing is measured at the aircraft. The two navigational aids to consider here are NDBs, which are non-directional beacons which provide a signal to the ADF, automatic direction finders, in our aircraft, and airborne weather radar. This plotting problem would occur if the chart convergence between the aircraft and the ground station were large enough to significantly alter the bearing. Let's see why. The bearing is measured at the aircraft. Let's, at this stage, forget about problems of magnetic variation and relative bearing. Assume that we have made any corrections required and are now dealing with a true bearing from aircraft to ground station. This will have been measured at the aircraft position, using the local direction of true north, that is to say, directly up the meridian which the aircraft is on. In this example, it is 060 true. We will then need to add 180 degrees to get a bearing of 240 degrees to plot from the ground station. However, we will be putting our protractor down at the ground station position. The ground station's meridian is not parallel to the aircraft's meridian. If we simply plot the reciprocal from the local true meridian at the NDB, the bearing will be in error by the amount of chart convergence between the two positions. We could calculate the convergence between the two meridians and add it to our angle to plot. But, in practice, it is much simpler to draw a parallel construction line, which we will call the false meridian, and plot the simple reciprocal from that. This is the method that is actually used in practice if the chart convergence is large enough to make the correction worth applying. Normally, we would not apply it to convergences of 1 degree or less. So, let's summarize these plotting rules. The radio bearing may be measured either at the aircraft or the ground station. These are the rules for plotting bearings. For bearings measured at the ground station, that is, VDF or VOR, first, apply magnetic variation at the ground station, if necessary. Then, simply plot the bearing from the ground station. For bearings measured at the aircraft, that is, ADF or airborne weather radar, apply magnetic variation at the aircraft and heading to correct for relative bearing if required, in order to obtain a true bearing from aircraft to ground. Reciprocate. Plot the reciprocal from a paralleled false meridian at the ground station. This completes all of our work on the Lambert's chart. We are now going to study the third of our series of the charts most commonly used in aviation, the polar stereographic projection. As before, we start with the reduced Earth. We add a light source. Note that, for this projection, the light source is at one of the poles, not the centre. A sheet of flat paper representing a plane surface is placed at the other pole, exactly perpendicular to the Earth's axis, and the light is projected. You can see that point A has an image at A1, point B at B1, and so on. The result looks like this. The scale is correct near the pole, but expands as we move away. This projection is used to create the polar stereographic chart. Of the charts that we consider, this is the only perspective projection. It is exactly as the light falls. By choosing the opposite pole instead of the centre of the Earth for the light source, we have produced a projection that is already orthomorphic, and so there is no need for any mathematical adjustment. This diagram is based on having the light at the South Pole. It shows the geometry of how the projection is generated. You can see that meridians, which appear on the globe like this, will appear on the chart like this. The parallels will be concentric circles. However, they are not evenly spaced. The chart distance between equal changes of latitude is expanding as we move away from the pole. We can arrive at an equation for the rate of scale change, but in order to do so, we first need to introduce the idea of the co-latitude. We know that latitude is the angle measured from the equator in the direction of the pole. Co-latitude is the angle measured from the pole towards the equator. Latitude and co-latitude must add up to 90 degrees. So that if the latitude were, say, 60 degrees, the co-latitude would be 30 degrees. Now consider the two light paths shown in the diagram. Let's take the one which passes through the equator. If the latitude is 0, then the co-latitude is 90 degrees. Now let's look at the angle that the light path makes with the Earth's axis. From the pole to the centre of the Earth is 1 Earth radius. And from the centre of the Earth to the equator is also 1 Earth radius. So we have an isosceles triangle, with the angle that the light path makes with the Earth's axis having a value of 45 degrees. The angle that the light path makes with the Earth's axis is always half the co-latitude. This is a general result and is true for any co-latitude. For instance, if the co-latitude is 30 degrees, the angle that the light path makes with the Earth's axis will be 15 degrees. The scale expansion along the sheet of paper is therefore a function of the co-latitude. You are not required to remember the details of the above explanation, but you should remember the equation that results, which is that scale expands away from the pole at a rate of the secant squared of half the co-latitude. The result is a projection in which the distance between concentric circles of latitude is expanding as we move away from the pole. The projection can be used to show all of one hemisphere, as here, where you can see the equator. In fact, it would have been possible to extend the coverage 10 degrees further south, taking in some of the southern hemisphere, and the chart is still fairly undistorted and usable. This makes the polar stereographic a very good strategic planning chart on a global scale. We're now going to consider all the important chart properties in the way that we did for our previous charts. This is our list and we'll go through them one by one. The first of these is scale. The scale is correct at the pole, where the paper touches the reduced Earth. Elsewhere, it expands as the secant squared of half the co-latitude. The equation for scale is that scale at any latitude equals the scale at the pole times the secant squared of half the co-latitude. We will now show how this equation works by calculating how the scale changes between the pole and 78 north. This is to show a worked example of the calculation, although, as we shall see, 78 north also has a particular significance. We should emphasize that these calculations are not required by the examination syllabus. This is simply a demonstration. If the latitude is 78 north, what is the co-latitude? If the latitude is 78 north, the co-latitude will be 12 degrees. So half the co-latitude will be 6 degrees. Let's substitute it into the equation. Secant squared 6 degrees is just another way of saying the secant of 6 degrees times the secant of 6 degrees. And, as we know, secant is 1 over cosine, so we can substitute in order to have the number 1 as the numerator. Let's assume the scale at the pole to be 1 to 1 million. We can look up the cosine of 6 degrees on our calculators. Rounded to 4 figures, it's 0.9945. And if you now multiply out the right-hand side, you'll find that you get a scale of near enough 1 to 990,000. A scale of 1 to 990,000 is within 1% of our original scale at the pole of 1 to 1 million. So, between latitudes 90 and 78, the scale is within 1% of the scale at the pole, which we take to be a constant scale chart. A similar substitution can be carried out for a latitude of 70 degrees. Out to this latitude, the scale is within 3% of the scale at the pole. This constancy of scale makes the polar stereographic projection an almost ideal map for flying in polar regions. Polar routes have become much more common now than previously because of 3 recent developments. Firstly, there is the breakdown of former political rivalries, with greater freedom of overflying rights. Secondly, there is the advent of aircraft of long range and endurance and their associated ETOPS regulatory procedures. And thirdly, there is very wide availability of flight management computers based on inertial navigation systems. It has now become common to use polar routes, which are often shorter, and some go very close to the pole indeed. Imagine a route like this, which is typical. Take the 1% scale zone. The co-latitude of 78 north is 12 degrees. There are 60 nautical miles to a degree, so the distance from the pole to latitude 78 north is 720 nautical miles. If the aircraft is entering on one side and leaving more or less on the opposite side of the circle, the total distance in the 1% zone is around 1400 nautical miles. At typical jetliner speeds of around 450 knots TAS, that is approximately 3 hours flying time. A chart which can be considered constant scale and allows measurement of distance with a ruler for over 3 hours flying is a very useful projection. If the 3% zone is taken, the same chart can be used for 5 hours. This projection is orthomorphic. Meridians are straight lines originating from the pole. Parallels of latitude are circles centered at the pole. The expansion is at the same rate in any direction from a point. We have already covered the graticule in discussing orthomorphism. As we said, meridians are straight lines originating from the pole. parallels are concentric circles centred on the pole, with their spacing increasing as the secant squared of half the co-latitude. The way that shapes will be affected is fairly obvious. Because of scale expansion, shapes and areas will be more distorted the further the distance from the pole. You can see that Africa looks too large compared with Europe and the northern part of the United States. And on this southern hemisphere chart, you can see that the northern part of the South American continent looks too wide. This chart has a convergence factor of 1. This leads to some interesting properties which we will explore in more detail in a later lesson. The parallel of tangency is actually a point of tangency. In this case, it's the pole with a latitude of 90 degrees. The angle of the cone is, as with any cone, twice the parallel of tangency. The cone angle is therefore 180 degrees, which means that it has been flattened into a plane surface. The normal rules apply. The sine of 90 degrees is 1. This chart, therefore, has an n factor of unity, which is another way of saying that there is no segment missing when we flatten the cone. It is already flat. This means that the chart convergence is always equivalent to the change of longitude between 2 points, whatever their latitude. We can show it with this proof. This is a polar stereographic chart, looking down on the North Pole, with the Greenwich meridian coming in from the 6 o'clock position. Take 2 meridians, let's say 70 degrees apart. Because 1 degree of change of longitude is always 1 degree of chart convergence on this projection, there will be an angle of 70 degrees between them at the pole. Now draw a track joining them, not necessarily at the same latitude. Now, let's look at the geometry of this triangle. The internal angles of any triangle have to add up to 180 degrees. We have 40 degrees here and 70 degrees here, which add up to 110 degrees. Subtract this from 180 and that gives us 70 degrees here. The line AB is straight line track, and a straight line also has an angle of 180 degrees. So the supplementary angle, in other words the track angle at B, is 180 minus 70 degrees. This is a track of 110. The original track was 040. So the track angle must change by the amount of the chart convergence, which is also the change of longitude on this projection. There are just 2 more points before we leave chart convergence for this lesson. We shall return to it later. The first is that the meridians are straight lines. Therefore, chart convergence is constant all over the chart, whatever the latitude. The second is that there are only 2 places on Earth where 360 degrees of angular change of the meridian is equal to 360 degrees of longitudinal change. These are the North and South poles. So, chart convergence is correct only at either pole. Rhumb lines behave exactly like those on a Lambert's projection. Meridians are straight lines originating from the pole. Other rhumb lines are curves concave to the nearer pole. It's obvious in the case of a parallel of latitude. However, any rhumb line except a meridian will still be curved concave to the nearer pole. Great circles are also similar to the Lambert's chart in that they are concave to the parallel of origin. However, in the case of the polar stereographic projection, the parallel of origin is the pole. Look at the diagram. Again, it is looking down on the North Pole with the Greenwich meridian coming in from the 6 o'clock position. It shows 3 lines at 50 north and 3 more at 70 north. The blue represents a straight line on the chart. The green lines are great circles. And the red ones are rhumb lines. This demonstrates that the great circles are concave to the nearer pole, but their concavity becomes less as we approach the pole. If we compare the great circles at 50 north and at 70 north, you can see that the great circle is closer to a straight line as the latitude increases. In fact, for all practical purposes, a great circle may be taken as a straight line at latitudes of 70 degrees or more. The primary use of the polar stereographic projection is as a polar plotting chart. Some meteorological charts also use it. And it can also be used for planning purposes on a global scale, as more than half the globe can be shown on a single sheet. Examiners will expect you to remember the primary use as a polar navigation chart. So, let's summarize what we've covered in this lesson. We looked at scale. It's correct at the pole. Elsewhere, it expands as the secant squared of half the co-latitude. Scale is within 1% of the polar scale out to 78 degrees latitude, and is between 1 and 3% of the polar scale between 78 and 70 degrees latitude. The projection is orthomorphic. All charts used for navigation must be. In fact, this one is both orthomorphic and perspective, and is the only one of our projections which is. We've seen the graticule. Meridians are straight lines originating from the pole. Parallels are concentric circles centered on the pole, with the distance between them increasing as the secant squared of the co-latitude. We looked at shapes. They become more distorted as the distance increases from the pole. Chart convergence will be examined in slightly more detail in the next lesson. It's correct, which means the same as on the Earth at the pole. It's constant across the chart, and the chart convergence between any two meridians is equivalent to the change of longitude whatever the latitude. In other words, the n factor is 1. In considering rhumb lines, meridians appear straight. But other rhumb lines are curves concave to the nearer pole. Great circles also include meridians, which appear straight. But generally, great circles are curves concave to the nearer pole. However, they have less curvature than rhumb lines, and they become nearer to straight lines as they approach the pole. They may be considered, for all practical purposes, as straight lines at latitudes greater than 70 degrees.
We have already studied how the polar stereographic projection is produced. This led on to an examination of its properties. Let's re-examine chart convergence. It's correct, in other words the same as Earth convergence at the pole. The meridians are projected as straight lines. Therefore, chart convergence is constant all over the chart, whatever the latitude. The chart convergence is always equivalent to the change of longitude between 2 points, whatever their latitude. This is the same thing as saying that the n factor is 1. We then showed by a geometrical proof that the chart convergence, or change of straight line track, is always equivalent to the change of longitude. We're now going to go on and show this idea in operation with a couple of practical examples. This will then lead on to solving some typical examination questions. Let's look at a situation in the Northern Hemisphere. Here are the land masses and the graticule. We're going to fly from Miami to the southern tip of India. Miami is at longitude 083 west. See where the Greenwich meridian is, and where the 90 degrees west meridian is. So we can now label Miami at 83 west. Now when you look at the 90 east label, you can see that our destination in India is at longitude 085 degrees east. The change of longitude is 168 degrees, but which way, eastwards or westwards? Going from a westerly longitude via the Greenwich meridian to an easterly longitude is obviously an easterly track direction, so it's 168 degrees eastwards. What effect will this have on the track direction? Will it increase or decrease? Do you remember this diagram from our basic study on great circles? The top and bottom halves of the diagram represent the northern and southern hemispheres, but the left and right sides are not hemispheres. They show you the direction of the aircraft's track. For instance, the top right quadrant means that the aircraft is tracking eastwards in the northern hemisphere, so the track angle is increasing. The same rules apply to the direction of a straight line on any chart which has chart convergence. On our polar stereographic chart, our track angle from Miami to India will increase. Looking at the local meridian at Miami, you can see that the initial track is northwards. Accurately measured, it's 004 degrees true. It should now increase by 168 degrees by the time it arrives at the destination. So the inbound track to the destination should be 172 degrees true. Have a look at the track relative to the local meridian in southern India. You can see that it is clearly about 172. The straight line track angle has changed by the change in longitude between departure point and destination. The theory works when demonstrated in practice. Now for an example in the southern hemisphere. Again, we have the land masses and the graticule. We shall go from Cape Town to New Zealand. This time, the Greenwich meridian is at 12 o'clock. And 90 east is at 3 o'clock. That puts Cape Town at longitude 022 east. And our destination at longitude 175 east. This is a change of longitude of 153 degrees eastwards. Going back to our DIID diagram, if we are in the southern hemisphere and tracking eastwards, the track angle must decrease. You can see that the initial track angle from Cape Town is approximately south-southwest. Measured accurately, it is 169 degrees true. This should decrease by 153 degrees. So the inbound track to New Zealand should be 016 degrees. If we rotate the diagram to put the destination at the top, we now have the local meridian at New Zealand at the top. You can see that the track angle is about 016 degrees. As before, the theory works in practice. The straight line track angle has changed by the change in longitude between departure point and destination. How will your examiners test your understanding of these ideas? Here are some typical examples. What is the initial straight line track from A at 75 north, 60 west to B at 75 north, 60 east? You are given four options: A, 090 degrees true, B, 030 degrees true, C, 120 degrees true, D, 330 degrees true. You cannot solve these types of problem without a diagram. Both the latitudes are at 75 north, so draw a polar stereographic reticule looking down on the North Pole. Firstly, put in the North Pole and the parallel of latitude of 75 north. As we're at the North Pole, put the Greenwich meridian in, running up from the 6 o'clock. If it were the South Pole, it would be the 12 o'clock. You'll find that this is a useful convention to get used to, especially when dealing with grid problems later. Now plot in position A at 75 north, 60 west, and B at 75 north, 60 east. Now draw in the two meridians and the straight line track. The question is, what is the initial straight line track? They are asking for the track angle at A. The line between A and the North Pole is the local meridian. It defines local true north. The initial straight line track is therefore the angle between this meridian and the line from A to B. This is what we are trying to find. You could, if you drew it accurately, simply solve it by measuring the angle with your protractor. It is pretty obvious that of the options available, the answer must be 030. However, this is not what the examiners have in mind. They are expecting a solution based on simple geometry. The change of longitude from 60 west to 60 east is 120 degrees. As this is a polar stereographic chart with its convergence equal to the change of longitude, the angle at the apex of the triangle is also 120 degrees. The internal angles of any triangle must add up to 180 degrees. If one of the angles is 120 degrees, that leaves 60 degrees to be shared between the other two. However, A and B are both at 75 north. That makes this an isosceles triangle. The 60 degrees is shared equally between the two base angles. Therefore, they are both 30 degrees. Track is defined as the angle measured clockwise from local true north. Therefore, our initial track angle is 030. Let's explore this idea of polar stereographic chart convergence a bit further. What if the question had taken exactly the same situation, but had asked you to find the initial straight line track from B to A? In that case, you would have been looking for this angle. Using exactly the same calculations, it would have been 30 degrees. However, the track angle would not have been the same. The line from B to the pole defines the local meridian, or direction of true north. But we measure track angles clockwise from the meridian. So what does that make the track angle at B when going towards A? You should have come up with the answer 330 degrees true. So the initial track from B to A is 330. Now another question for you. Suppose the aircraft had travelled from A to B, as in the original question. What would be the final track angle as it passes over B? You should have come up with the reciprocal of 330, which is 150 degrees true. So let's think about this a bit further. We left A on a track of 030 and arrived over B on a track of 150. How much has the track angle changed? The track has changed by 120 degrees, which is exactly the value of the change of longitude, and therefore the chart convergence. There is another way altogether that you could have solved this problem. It comes from the idea which we explored when considering the Lambert's chart. The difference between a straight line and a rhumb line is always half chart convergence. Considering the route from A to B, the rhumb line will be the parallel of latitude. So what will the initial track angle be? Parallels of latitude can only have two tracks. They either go due east or due west. The initial rhumb line track angle from A to B must be 090. We know that the chart convergence is the same as the change of longitude. It's 120 degrees. Therefore, the difference between the rhumb line and the straight line must be half that. It's 60 degrees. So measuring 60 degrees anti-clockwise from 090, the initial straight line track angle is 030, the same result as when we solved it using triangles. Finally, before leaving this example, let's look at the initial track angle from B to A using this half-chart convergence method. Here is the rhumb line track. What is its track angle? It's obviously 270 degrees true because it's a parallel of latitude going westwards. Again, half-chart convergence is 60 degrees. So again, measuring 60 degrees clockwise from 270, the initial straight line track angle is 330, the same result as before. Let's look at another question now. Here's example 2. At what longitude does the straight line track from A at 70 north, 40 west to B at 70 north, 80 east on a polar stereographic chart reach its highest latitude? The four option answers are A, 40 west, B, 30 west, C, 20 east, D, 40 east. As before, draw a diagram. Again, the latitudes at A and B are the same, so you can draw a parallel of latitude. And again, because we're in the northern hemisphere, draw the Greenwich meridian coming in from the 6 o'clock position. Now put A at 40 west and the line joining it to the pole, and B at 80 east with its meridian. Now going back to the question, where will the straight line track from A to B reach its highest latitude? The highest latitude occurs when the co-latitude distance is shortest. This must occur when the track is directly abeam the pole. You can see that the distance here at the right angle is shorter than here or here. The two latitudes are the same, so we are dealing with an isosceles triangle again. Therefore, the line which is perpendicular to the base must be the bisector of the apex angle. If the angle from 40 west to 80 east is 120 degrees, then each half of the bisected angle at the apex must be 60 degrees. So you can either count 60 degrees eastwards from 40 west, or 60 degrees westwards from 80 east. But either way, you come up with the same answer. The highest latitude is at the mid-meridian, which is at 20 east. This idea that a track is at its highest latitude when it is perpendicular to the meridian can be useful in solving track angle problems. We have encountered a similar idea before, right at the start of the course when we were studying vertices. The vertex is the point on the great circle when it is closest to the pole, and the track is always 090 or 270. This idea is sometimes used by examiners. Take this question. On a polar stereographic chart, a line is drawn from position A at 70 north, 102 west, to B at 80 north, 006 east. The point of highest latitude along this line occurs at longitude 35 west. What is the initial straight line track angle from A to B measured at A? As usual, you are given 4 option answers, which are A 049 degrees true, B 077 degrees true, C 229 degrees true, D 023 degrees true. As always, draw yourself a sketch. With just the departure and destination points and the meridians, it should look like this. If you couldn't think of any other way, you could do it by scale drawing. This is the angle that they are looking for. If you draw the angles accurately, making sure that the radius to 70 degrees is twice as long as that at 80 degrees, you will see that, of the options given, 023 is the only possible answer. However, again, this is not what the examiner is expecting. He has given you the information that the point of highest latitude occurs at longitude 35 west. We should use this. Let's put the information into the diagram. Now let's consider this smaller triangle. Angle C is a right angle. The examiner has effectively told us this. Angle B is bounded by longitudes 35 west and 102 west. So the change of longitude is 67 degrees. As this is a polar stereographic chart, angle B is therefore 67 degrees as well. The internal angles of any plane triangle must add up to 180 degrees. There are 90 here. That leaves the other 90 to be split between A and B. 90 minus 67 is 23. So the angle at A is 23 degrees. And, as before, the line from A to the North Pole is a meridian. So measuring clockwise, we get a track angle of 023 degrees true. We now summarize this lesson. Many exam questions are based on the idea that, for the polar stereographic projection, the track angle change between any 2 points is exactly equal to their change in longitude, whatever their latitude. We showed that this was true in practice with an example in the Northern Hemisphere and with another one in the Southern Hemisphere. We then explored the angles around a straight line track where the start and finish latitude were the same. We were able to calculate the initial track angle by using the idea of adding the angles in an isosceles triangle, or alternatively, by using the concept that the angle between the rhumb line and the straight line is half the chart convergence. We then established that the highest latitude of a straight line track occurs when the track cuts its meridian at right angles. Finally, we used this principle of the right angle occurring at the highest latitude to solve a problem where the start and finish latitudes were not the same. We now move on to the fourth of the projections which are commonly used in aviation, the transverse Mercator. In the normal or direct Mercator, the cylinder is aligned perpendicular to the equator. Another word for perpendicular is normal. Over most of the Earth, it suffers from the problem of excessive scale expansion. However, out to 8 degrees north or south of the equator, the scale expansion is within 1% of the scale at the equator. This gives us a strip 480 nautical miles either side of the equator, within which the scale can be regarded as constant. The problem is that there are not many routes which follow a parallel of latitude fairly close to the equator. It might be useful from Quito to Manaus, or perhaps Libreville to Kampala, but in terms of world traffic, this is still pretty limiting. However, consider what happens if we wrap our cylinder transversely, that is, parallel to the equator. This will now give a projection which contains a vertical band of constant scale. This is far more useful. We can choose whatever longitude we want for the meridian of tangency. For instance, Cairo to Johannesburg, or Istanbul to St. Petersburg. We now have a projection which is completely correct along the whole length of the meridian of tangency, and is within 1% of the correct scale up to 480 miles either side of it. This gives a total width of 960 nautical miles, say approximately 1,000 for all practical purposes. This is a very useful chart. As with the normal Mercator, we start with a light source at the centre of the Earth, but now the cylinder is horizontal. In order to make the projection orthomorphic, Mercator's mathematical adjustments are applied afterwards. We select a datum meridian, depending on which part of the Earth we wish to map. We are going to cut away the bottom half of the cylinder. When the projection is completed, we are going to fold these two edges upwards to produce a flat piece of paper. We put in a parallel of latitude. Now let's try to imagine how this will appear on the flat sheet. Let's start by considering the distance from the North Pole down the data meridian. The cylinder is touching the reduced Earth along this line. The scale will be absolutely correct. The length of the line on the paper will be the same as the length of the line on the globe. But what if we look at this parallel of latitude at a longitude which is 90 degrees removed? This is the distance from the pole to the parallel of latitude on the globe, whilst this is the distance on the cylinder thrown by the shadow from the light source. You can see that the line along the top of the cylinder is longer than the line down the cylinder. This produces an elliptical shape. Looking down on the flat chart from above the North Pole, if this is the data meridian, with its 1,000-mile wide strip of constant scale from the equator over the pole down to the equator on the other side, the meridian at 90 degrees to it, which was the top of the cylinder, is here, and the parallel of latitude which formed our ellipse is here. What if we had chosen a higher latitude? Suppose our parallel of latitude had been nearer the pole, here. In that case, there would have been less scale expansion along the top of the cylinder. The result would still have been elliptical, but much less so. In fact, it would have looked pretty much like a circle. How is the equator projected? Imagine the light at the centre of the Earth shining through the equator. It will throw out a horizontal line stretching all the way along the cylinder's length. There will be one of these on the near side of the cylinder as you are looking at it, and another one at the further edge of the paper. When the paper is folded flat, these two lines will appear like this. And finally, let's look at the meridians other than the data meridian, and the one at 90 degrees to it. These will be projected as complex curves. We will look at what determines the shape of the curves in a later part of this lesson. We are now going to consider all the important chart properties in the way that we did for our previous charts. This is our list, and we'll go through them one by one. The first of these is scale. We're not required by the exam syllabus to mathematically calculate scale change, so we'll just deal with the principles. The scale is correct everywhere along the data meridian. Taken all the way around the Earth, to include the antimeridian, this gives a line 21,600 nautical miles long, where the scale is completely correct. This line is the centre of a strip almost 1,000 nautical miles wide, in which the scale is within 1%. The projection has had Mercator's corrections applied to the original light source image, so it is now mathematical and non-perspective.
The scale will therefore expand in an east-west direction in a secant relationship, just as the normal Mercator expanded in a north-south direction as the secant of the latitude. However, there is no direct equivalent of latitude in the east-west sense. As you will recall, longitude works on a different principle. Latitude is in parallels, like slicing a pineapple. Longitude works in radial angles, like segmenting an orange. Scale expands away from the data meridian in proportion to the angular great circle distance in the east-west direction. We know that this particular chart will be orthomorphic. It is simply a Mercator, which we already know to be orthomorphic, with the cylinder rotated to a horizontal position instead of a vertical one. The original perspective light projection would not be orthomorphic, but with Mercator's secant expansion rule applied laterally instead of vertically,
the projection becomes orthomorphic. How will the graticule look? Let's consider the data meridian first. This is a straight line on the projection.
Let's also look at the meridian perpendicular to the datum meridian. This runs along the top of the cylinder. This is also a straight line on the projection. And we have already noted that the equator appears as two straight lines. Now let's consider the other meridians. We know that the projection is orthomorphic. We have adjusted it so that it is. Therefore, meridians must cross parallels at right angles. Near the pole, parallels are close to circular. So the meridians will emerge radially from the pole in a very similar way to the polar stereographic. However, at lower latitudes, the parallels become more elliptical. The meridians must therefore curve so that they cross this parallel at right angles too. And on this projection, the equator is a straight line. The meridians must cut these two at right angles. This therefore must make a curving line. The three right angles which the circle, the ellipse and the equator make with the meridian mean that, unless it is one of the two cases of the datum meridian and the meridian at right angle to it, the meridian is a complex curve. So that's the meridians dealt with. What about the parallels? We have already discussed this when dealing with how the projection is produced. We decided that parallels of latitude are ellipses, very close to circular near the poles, with the degree of ellipticity increasing as we move away from the pole. At the equator, the ellipses have become straight lines. Strictly speaking, for a mathematician, this is the ultimate case of the ellipse, with the ends out at infinity and the elongation such that the sides have become parallel at the point where we are viewing them. However, for most non-mathematicians, this is rather an abstract concept, so as pilots, we simply say that the equator is represented as two parallel straight lines. Therefore, to summarize, the datum meridian and the meridian perpendicular to it are straight lines. All other meridians are complex curves. Parallels are ellipses which become more elliptical with the distance from the pole. And the equator appears as two straight parallel lines. Shapes are fairly easily dealt with. With the normal Mercator, scale expansion leads to shape distortion as the north-south distance from the equator increases. However, our cylinder is horizontal, not vertical. Therefore, on this projection, scale expansion leads to shape distortion as the east-west distance from the datum meridian increases. However, this is not usually a problem, as the chart is not normally used outside the 1% east-west scale expansion band. If we need to go further east or west, we use a chart with a different datum meridian. Chart convergence is complicated on this projection because it constantly changes. This is because meridians are mostly complex curves which constantly change direction. Near the pole, the parallels of latitude are not very elliptical. In fact, they are virtually circles. So as we have just said, the meridians will emerge radially from the pole in a very similar way to the polar stereographic. At the pole, therefore, the chart convergence factor is 1 because, just like the polar stereographic, there are 360 degrees of longitude represented by 360 degrees of angle on the chart. So the chart convergence is correct at the pole, which means that it is the same as the Earth convergence at the pole. Now consider the situation at the equator, which is depicted as two straight lines. As the meridians must cut these at right angles too, They are all parallel to each other at the equator. This means that the chart convergence is correct at the equator as well, because Earth meridians are also parallel to each other at the equator. So we can sum up chart convergence by saying that it is correct at the pole and the equator, but not elsewhere. How will rhumb lines appear on this chart? They follow the same pattern as meridians. The datum meridian is a straight line. The meridian perpendicular to it also appears as a straight line, and the equator appears as two straight lines. All other rhumb lines appear as complex curves. The depiction of great circles is fairly similar to rhumb lines. The datum meridian is a straight line. The meridian perpendicular to it is a straight line, and the equator appears as two straight lines. However, another family of great circles also form straight lines. Imagine the datum meridian like this. Now consider a great circle with its vertex on the datum meridian. In other words, crossing it at right angles. If we rotate the cylinder and Earth together so that we are looking at it end on, we see this. Now try to imagine what will happen when we shine the light at the centre. The projected shadow will appear as a straight line along the cylinder parallel to the projected equator. This is shown here on the projection. So, great circles are complex curves, except for the datum meridian. The meridian perpendicular to it, the equator, and great circles perpendicular to the datum meridian. This projection has three main uses, but one in particular should be remembered for examination questions. Its primary use is for large-scale mapping of long, thin countries with a large north-south extent and less east-west extent. The UK Ordnance Survey, for instance, uses a transverse Mercator projection, as can be seen from this note on the side of a 1 to 50,000 Land Ranger series. The CAA quarter-million topographical air charts of the United Kingdom series, which are widely used by helicopter and general aviation pilots, are also based on this projection. However, the transverse Mercator projection can also be used for flying routes with a large north-south extent and less east-west extent. And it is actually a better projection for polar flying than a polar stereographic chart, provided that the route is along or very close to the datum meridian. The scale is completely correct all along the datum meridian, and within 1% over a 1,000-mile wide strip. However, examiners are likely to concentrate on the first application, large-scale mapping of long, thin countries with a large north-south extent and less east-west extent. So let's summarize these properties. We looked at scale. It's correct along the datum meridian. Elsewhere, it expands as the secant of the great circle arc distance in the east-west direction. The chart is orthomorphic. It follows Mercator's rules for construction of the graticule. The graticule is complex. The datum meridian, the meridian perpendicular to it, and the equator are straight lines. Other meridians are complex curves. Parallels of latitude are ellipses, except for the equator, which appears as two straight lines. Shapes follow the pattern of a direct Mercator, except that the distortion increases with the east-west distance from the data meridian. The chart convergence is also complex, but it is correct at the pole and the equator. Rhumb lines are generally complex curves, except for the data meridian, the meridian perpendicular to it, and the equator. Great circles are also complex curves, except for the data meridian, the meridian perpendicular to it, the equator, and great circles perpendicular to the data meridian.
The last lesson was on the transverse Mercator projection. You should make sure that you are familiar with it before coming on to this one, because the oblique Mercator projection is an extension of the same ideas. One of the problems with the normal or direct Mercator was that the constant scale area was limited to a band of 960 nautical miles wide, that is, 480 nautical miles either side of the equator. Whilst we are also limited to 480 nautical miles either side of the data meridian on the transverse Mercator, this is less of a problem. There is only one parallel of latitude, which is a great circle, whereas there are an infinite number of meridians and their corresponding anti-meridians which can be used for the datum great circle. Therefore, if a flight involves a departure of more than 480 nautical miles east or west of the data meridian, we simply change chart to another transverse Mercator, which uses a different data meridian. By changing charts, we can fly all the way around the Earth if necessary in an east-west sense using transverse Mercators. You cannot do this north or south with the direct Mercator. However, there is a better way. Suppose that the route is from London to Nairobi. The shortest route between these 2 points is the Great Circle joining them. If the Great Circle route between 2 points is chosen as the Great Circle of tangency, and the cylinder is wrapped around this, the result is an oblique Mercator projection. This new Great Circle of tangency, which is often referred to as the false equator, will have correct scale all along its length, and will be within 1% out to 480 nautical miles either side of the centre line. This gives a strip of constant scale which is effectively 1,000 nautical miles wide, and of a length which can include the whole of the Earth's circumference. The Great Circle is a straight line, and any other great circle within the cover of the map is, for all practical purposes, also a straight line. If we take the false equator strip and lay it flat, and then cut it up into usefully sized segments for a convenient chart, we get a sheet with the false equator along the centre line. With less than 1% scale error anywhere on the chart, provided the scale chosen gives sides which are not more than 480 nautical miles away from the centre, on which straight lines may be taken to be great circles. This has virtually all the advantages we require and almost no drawbacks. It is true that calculation of chart convergence is complex, but this is not usually needed in practical flying. For this reason, use of the oblique Mercator is becoming more common. Jeppesen still use mainly Lambert projections, but nearly all AirRAD en route charts are now oblique Mercators. The main use of the oblique Mercator chart is for flying specific great circle routes. However, it also makes a very good general purpose en route chart, plotting chart, or radio nav chart. The graticule looks like this. It may not look it, but it is in fact orthomorphic. The actual relationship of the latitude and longitude graticule to the great circle of tangency, the so-called false equator, will vary according to the choice of false equator, but the general pattern is as we see here. We will now examine the chart properties in the usual way. This is the list which is of interest to us. We'll start with the graticule. It is, as we have already described, complex and apparently irregular, but, in fact, orthomorphic. Next is scale. It expands as the secant of the great circle distance from the great circle of tangency. However, it is constant, or very near to constant, close to the false equator, which is where it will be used. Convergence is correct along the great circle of tangency, and also at the poles and equator. Rhumb lines will be complex curves. However, this chart would not normally be used for rhumb line flying. Great circles are complex curves, but may be taken as straight lines close to the great circle of tangency. Therefore, for all practical purposes, a straight line on the chart is a great circle. Let's summarize this lesson. If the great circle route between 2 points is chosen as the great circle of tangency, and the cylinder is wrapped round this, the result is an oblique Mercator projection. This new great circle of tangency, which is often referred to as the false equator, has correct scale all along its length, and is within 1% out to 480 nautical miles either side of the centre line. The great circle is a straight line, and any other great circle within the cover of the map is, for all practical purposes, also a straight line. The main use of the oblique Mercator chart is for flying specific great circle routes. However, it also makes a very good general purpose en route chart, plotting chart, or radio nav chart. The graticule is orthomorphic. This projection has all the advantages we require and almost no drawbacks. This completes our study of the oblique Mercator and, with it, our study of maps and charts.
This is the first of a series of 4 lessons on time. Your first reaction may be that this seems like rather a lot. And why do pilots need to know about time anyway? The 2 most practical reasons are that, firstly, you should know why different countries keep different times, and how to find what the standard time is in any country you may land in. Most laymen, and some pilots, when using the PA to passengers, call this the local time, but the correct term is standard time. Secondly, you need to be able to work out when it gets dark in different parts of the world at different times of the year, or when it gets light in the morning, especially if the destination airport does not have airfield lighting. These are good practical reasons. However, our measures of time are based on the Earth's rotation about its own axis, the Earth's rotation around the Sun, and the movement of the solar system in our galaxy. We therefore need to know something about elementary astronomy. The Earth is one of 8 major planets which orbit the Sun. We are going to look at the pattern of these orbits, because they affect how we define a day and a year. The laws governing orbits were worked out by Johann Kepler in the 17th century. Previously, it had been assumed that planetary orbits were circular, but this hypothesis did not tie in with actual observations. Kepler's first law is that the orbit of each planet is an ellipse, with the Sun at one of the foci. Let's start by explaining what an ellipse is and what these foci are. We'll begin with a circle. We define a circle by starting with the centre, then producing a radius of a constant length, and then we rotate the radius through a revolution. With an ellipse, we have 2 starting points, not 1. These are called foci, which we'll label F1 and F2. If the distance from F1 to the edge and back to F2 always stays the same, then by definition we have an ellipse. To make it a planetary orbit, we'll put the Sun at F1. F2 can now be ignored. As we now have an elliptical orbit, there will be a closest point of approach to the Sun and a furthest point. The near point is called perihelion. It comes from two Greek words, peri, meaning near, and helios, meaning sun. Perihelion occurs on or near the 4th of January. The average distance from the Sun to the Earth over the year is 93 million miles, or 150 million kilometres. However, at perihelion, that distance reduces to about 91.5 million miles. We do not use nautical miles when discussing distances in space. The furthest point is called aphelion. It occurs on or around the 3rd of July. At that point, the distance from the Earth to the Sun is at its maximum of about 94.5 million miles. In the Northern Hemisphere, early January can be one of the coldest times of the year, but this is the time when the Earth is closest to the Sun. The changing distance from the Earth to the Sun makes very little difference to the amount of heating, so the changes in the seasons must be caused by something else. We now move on to Kepler's second law. This describes how a planet's speed changes during its orbit. The orbital velocity is constantly changing with the distance from the Sun. It is fastest when near perihelion, and then slows down, reaching a minimum at aphelion. Kepler was the first person to find the relationship which describes how the speed changes. Kepler's second law is that the line joining the planet to the Sun, known as the radius vector, sweeps out equal areas in equal time. This is the radius vector. This is how far the Earth moves in a fixed time, such as a month, when near perihelion. However, when it is near aphelion, it is travelling slower. In the same time interval, the distance travelled round the orbit will be less. Kepler's second law states that if the grey shadings have the same area, the time will be the same. Let's remind ourselves of Kepler's first two laws. The first is that the orbit of each planet is an ellipse, with the Sun at one of the foci. And the second is that the line joining the planet to the Sun, known as the radius vector, sweeps out equal areas in equal time. Kepler's second law gives us a problem when it comes to explaining the length of a day. A day is one revolution of the Earth. We draw a line out into space from the centre of the Earth, passing through one particular meridian. As this line passes through some datum reference point, we call this meridian transit. Here we see a transit of the Sun. We start the clock. The Earth then rotates once until we have a second transit of the same meridian. We stop the clock, and the time taken is defined as 1 day. However, the length of our day will depend on what we take as our datum when measuring the transit. Remember that the Earth is orbiting whilst it rotates. We start off here, somewhere near perihelion, and will take some distant star as our datum. The distance can be regarded as being infinity for all practical purposes, so the light from it to the Earth is parallel, even though the Earth moves round its orbit. The Earth rotates once, and in that time moves a small amount round its orbit. It has turned through exactly 360 degrees with respect to space. This is called a sidereal day. However, what if we take the Sun as our datum? The Earth moves around its orbit. Therefore, if it rotates through precisely 360 degrees with respect to space, it will no longer be pointing at the Sun. In order to have a second transit with the Sun, it will need to rotate more than 360 degrees. In the time taken to make this extra turn, it will have travelled even further round its orbit. This is called an apparent solar day. Apparent is simply an astronomer's term, meaning that that's the way it appears to us. It is actually the true situation. An apparent solar day is always longer than a sidereal day. Now imagine the same situation somewhere near aphelion. The Earth would also have to rotate more than 360 degrees with respect to space in order to point back at the Sun. But because the orbital speed is slower, the time between successive solar transits is less than at perihelion. This difference in the length of an apparent solar day between perihelion and aphelion is half an hour. Over the year, the time between successive solar transits varies from about 23 3/4 hours to about 24 1/4 hours. This is nothing to do with changes in the hours of daylight and darkness, which is a separate problem. It actually means that the time from midday to midday, or midnight to midnight, changes over the year, if we take the Sun as our datum. What are the basic requirements for the length of a day to be useful to us? Basically, it should be related to the hours of daylight, so that 12 noon is always approximately halfway between sunrise and sunset. But it should also be of a constant length, so that an hour is always the same unit of time, whatever the time of the year. A sidereal day is of constant length. It always takes the Earth 23 hours and 56 minutes to turn through 360 degrees with respect to space. But it is not related to light and dark over the year. Suppose we are at perihelion. This is the meridian experiencing midday. If we use sidereal time 6 months later, that same meridian will now give us 12 noon on the clock, when it is actually the darkest period of the night. So clearly, a sidereal day does not meet the first of our requirements. It is not related to the hours of daylight. An apparent solar day is related to the hours of daylight, and 12 noon is halfway between sunrise and sunset. In a peasant society, which does not use clocks and does not need to keep time to the minute, this type of day has been used for centuries, and still is in many parts of the world. But you cannot base any simple mechanical device on a day which changes in length over the year. So an apparent solar day does not meet the second of our requirements. It is not of constant length. The solution is to average out the solar day over a year. We take a particular point on the orbit. We define the time that it takes the Earth to return to that point as 1 year. The Earth rotates 365 1/4 times in that period. We therefore take the total time in a year and divide it by 365 1/4 to arrive at the length of an average day. Another word for average is mean. This is where the term Greenwich Mean Time comes from. This gives us what we call our civil day. It is a mean solar day. It is sometimes helpful to think of the Sun travelling westwards around the Earth, rather than the Earth spinning eastwards. In the case of mean time, we consider the mean Sun to be circling the Earth every 24 hours. This is the basis of local mean time, which we will discuss in a future lesson. Greenwich Mean Time has been used by mariners for centuries and is based on the rate of Earth rotation. However, we now know that over time the Earth's spin rate is actually slowing down slightly. The most accurate clocks available are based on the vibration rate of a cesium atom, and these are now used as the basis for international time. Therefore, Coordinated Universal Time has replaced GMT. The difference amounts to about half a second a year, so to us as aviators it has no practical effect. When required, a leap second is introduced to bring the two into line, but most people are never aware of it. We will use the terms Coordinated Universal Time, or UTC, instead of GMT from now on. The civil day meets our two basic requirements, of being related to daylight and of constant length. However, it does mean that 12 noon on our clock is not usually the exact moment of meridian transit. The difference can be as much as about a quarter of an hour over the year. This difference is called the equation of time. This is a graph of how the difference changes over the year. The vertical axis is UTC, and the red curve indicates the time of meridian transit. As you can see, there are only 4 days a year when 12 noon on the clock is exactly as the sun crosses the meridian. The maximum difference is 16 minutes in November, when the real sun crosses the Greenwich meridian at 11:44 UTC. The next biggest peak is in February, when the difference is 14 minutes, as the real sun crosses the Greenwich meridian at 12:14 UTC. We also need to be able to define the length of a year. Again, there are several options. We could define with respect to a distant point in space. This gives us a sidereal year. A sidereal year is just over 365 days and 6 hours. However, the inclination of the Earth's axis changes by a very small amount year by year. To take account of this, and to have a year's length in phase with the recurrence of the seasons over the years, we need a very small adjustment. A tropical year keeps the seasons in phase. Its length is 365 days, 5 hours, 48 minutes and 45 seconds. But we cannot run a calendar and have a quarter of a day left over at the end of the year. The new year has to start with a new day at midnight, not 6 hours into January the 1st. Therefore, we have a calendar year of 365 days, except when it's 366. This explains why we have leap years. Suppose that this is the Earth's position in its orbit on the midnight ending the 28th of February one year. A year later, we are at the same calendar date at midnight, but the Earth is quarter of a day short of its previous position on the orbit. After 2 years, it will be 12 hours short. After 3 years, it will be 18 hours short. And after 4 years, it will be 1 day short of its previous position. We now add the 29th of February to the calendar, and the Earth catches up to its position of 4 years ago. The calendar is back in phase with the tropical year. If the difference between the calendar year and the tropical year were exactly 6 hours, that would be the end of the story. Unfortunately, it is 5 hours, 48 minutes and 45 seconds. Therefore, we need some fine adjustment. The normal rule is that if a year is divisible by 4, it is a leap year. So 2008 was a leap year, but 2009 was not. 2012 is, and so on. However, whole centuries, such as 1800 and 1900, are also divisible by 4. The first of our adjustments is that centuries are not leap years. This corrects most of the error, but there is still a tiny amount left. We need another adjustment. Every 4th century is a leap year. Thus, 1900 was not a leap year, but 2000 was. These rules may seem complicated, but you are required to know them. So let's try to put it simply. Every 4th year is a leap year, unless it's a century when it's not, unless it's a 4th century when it is. Let's summarize this lesson. You need to know about time because you should know why different countries keep different times, and how to find what the standard time is in any country you may land in. You also need to be able to work out when it gets dark in different parts of the world at different times of the year. In order to understand this, you need to know something about elementary astronomy. Kepler's first law is that the orbit of each planet is an ellipse with the Sun at one of the foci. There is a near point called perihelion, which occurs on or around the 4th of January. The actual date varies, depending on where we are in the cycle of the leap year. The far point is called aphelion, and occurs on or around the 3rd of July. Kepler's second law is that the line joining the planet to the Sun, known as the radius vector, sweeps out equal areas in equal time. Kepler's second law means that the length of an apparent solar day can vary between 23 3/4 hours to 24 1/4 hours over the year. A sidereal day would give us a constant length, but would not be related to day and night. The solution is the civil day, or mean solar day. However, using a civil day means that 12 noon on our clock is not usually the exact moment of meridian transit. The difference can be as much as about 1/4 of an hour over the year. The difference is called the equation of time. The maximum difference is 16 minutes in November. The next biggest peak is in February, when the difference is 14 minutes. A sidereal year is just over 365 days and 6 hours. A tropical year keeps the seasons in phase. Its length is 365 days, 5 hours, 48 minutes, and 45 seconds. A calendar year is 365 or 366 days. We use leap years to keep the calendar year in phase with the tropical year. The rules are that every 4th year is a leap year, unless it's a century when it's not, unless it's a 4th century when it is. That concludes this lesson on time. The next one will look at the Earth's tilt and the seasons. This is the second of our lessons on time. In the last one, we looked at Kepler's laws and the definitions of a day and a year. Kepler's first law is that the orbit of each planet is an ellipse, with the Sun at one of the foci. In the last lesson, we exaggerated the amount of ellipticity in our diagrams in order to make this point clear. But in fact, the difference in distance between perihelion and aphelion is only about 3% of the average Earth-Sun distance over the year. The Earth's orbit is almost circular, so the difference in distance at summer and winter has very little effect on the climate. In the northern hemisphere, early January can be one of the coldest times of the year, but this is at perihelion, the time when the Earth is closest to the Sun. So, as we suggested in the last lesson, the changes in the seasons must be caused by something else. The actual reason is the tilt of the Earth. All of the 8 major planets orbit in concentric ellipses very close to the same plane. For the Earth, this is called the plane of the ecliptic. However, the axes on which they spin are different. For instance, Mars is at 25 degrees off the perpendicular, Uranus is 98 degrees off, and Venus is nearly 180 degrees off. Earth is 23.5 degrees off the perpendicular of its ecliptic. This is what causes the annual changes in the seasons and the hours of daylight over the year. If we imagine the line between the centre of the Earth and the equator being extended out into space, we get another plane. This plane is called the equinoctial, and it is perpendicular to the Earth's spin axis. The angle between the ecliptic and the equinoctial is also 23.5 degrees. This is sometimes called the obliquity of the ecliptic. If this angle is 23.5 degrees, then the angle between the Earth's spin axis and the ecliptic must be 66.5 degrees. It is not that the Earth's actual tilt in space changes over the year. For instance, this is the situation on the 21st of June. The Earth's axis is inclined at 23.5 degrees to the ecliptic. This points to some fixed point in space, very close to Polaris, which can be taken as being fixed in space over a period as short as a year. 6 months later, the orientation of the Earth in space has not changed. It is still pointing to the same place in space near Polaris. What has changed, however, is its orientation relative to the Sun. In June, the line between the Sun and the centre of the Earth passes through latitude 23.5 degrees north. 6 months later, the line between the Sun and the centre of the Earth passes through latitude 23.5 degrees south. Over the year, the latitude directly under the Sun changes from 23.5 degrees north to the equator, to 23.5 degrees south, to the equator again, and back to 23.5 degrees north. If we look at it from an Earth-centred point of view, this is the apparent path of the Sun's overhead during the year. In order to define points in space, we need a celestial reference system similar to latitude and longitude. With latitude, we take the equator as the reference and measure the elevation angle to some point on the Earth's surface. For celestial measurement, we imagine the equator expanded out into space to form the equinoctial, and again measure the elevation angle to some point in space. This angle, which is the celestial equivalent of latitude, is called declination. Declination is the angle measured northwards or southwards from the equinoctial to a line joining the centre of the Earth to a body in space. It is the annual change of declination which causes the seasonal temperature changes. Let's consider the Earth on June the 21st. The Sun's diameter is more than 100 times greater than the Earth's. Therefore, relative to the Earth, the Sun's rays arrive on a broad front. Imagine a square cross-section of this heat and light, with sides of, say, 1,000 nautical miles. And another one down here. Each of these cross-sectional areas in space contains the same amount of heat. However, the angle at which the heat meets the Earth at latitude 23 north means that the heat is concentrated over the smallest possible area. At 23.5 south, it is spread over a much larger area, and so the heat is less concentrated. The Earth is rotating about its axis, which is tilted with respect to the Sun's rays, so that the area of heating remains at the same latitude over a day. This situation represents a northern hemisphere summer or a southern hemisphere winter. 6 months later, the Earth is at the opposite end of its orbit, and so the Sun is directly over latitude 23½ south. This gives us a southern hemisphere summer or a northern hemisphere winter. The latitude corresponding to the Sun's maximum northerly declination is 23½ north. It is known as the Tropic of Cancer. Similarly, the latitude corresponding to the Sun's maximum southerly declination is 23½ south. It is known as the Tropic of Capricorn. The regions of the Earth between these two latitudes are called the tropics, or the tropical zone, and they are the hottest parts of the Earth. The annual change of declination also causes the seasonal variation in the length of the hours of daylight. Again, consider the Earth on June the 21st. We'll take two positions on the Greenwich meridian, both experiencing local noon. One is at the equator, and the other at 40 north. The Earth now rotates for 6 hours, so that the local time for each of them is 6 p.m. You can see that the position at the equator is passing into darkness. However, the position at 40 north is still in daylight because of the inclination of the Earth. The Earth will have to rotate for another 1½ hours before this point passes into darkness, when the local time is 7:30 in the evening. This is a northern hemisphere summer, when the daylight hours are longer. However, for the southern hemisphere, it is winter. Their daylight hours are shorter. Here, the Earth has to rotate until only just after 4:30 in the evening for it to pass into darkness. 6 months later, the situation is reversed. You can see that the hours of daylight are now longer in the southern hemisphere. For them, it is summer, whilst the northern hemisphere has its winter. One of the consequences of these changes in declination is the phenomenon of midnight sun at high latitudes at certain times of the year. Consider the latitude of 66½ degrees north on June the 21st. The meridian facing the Sun is experiencing local noon. Local midnight occurs at its anti-meridian. Everywhere north of this latitude is in sunlight for a whole day. Similarly, everywhere south of 66½ degrees south is in darkness for a whole day. Higher latitudes give longer periods of continuous light or dark, but 66½ degrees north and south are the lowest latitudes at which it is possible to get at least one day of continuous light or of continuous dark, depending on whether it is summer or winter. They are therefore called the Arctic Circle and the Antarctic Circle. This is a graph of the annual declination of the Sun. As you can see, it looks sinusoidal in form. It would be a perfect sine wave if the Earth's orbit were truly circular. In practice, because the Earth's orbital ellipse is so close to circular, the graph is very close to sinusoidal. The declination of the Sun can therefore be considered to follow a sine wave, with a peak amplitude of 23½ degrees and a cycle of 1 tropical year. The Sun appears vertically above 23½ degrees south on the 21st of December. This is known as the Northern Hemisphere winter solstice and the Southern Hemisphere summer solstice. It then crosses the equator from south to north on about the 21st of March. This is known as the Northern Hemisphere spring equinox and the Southern Hemisphere autumn equinox. On the 21st of June, it will appear above 23.5 degrees north at the northern hemisphere summer solstice and the southern hemisphere winter solstice. And on the 21st of September, it crosses the equator from north to south at the northern hemisphere autumn equinox and the southern hemisphere spring equinox. These dates are not always exactly on the 21st of the month. This is partly because the precise date depends on the relationship between the year considered and the leap year cycle, partly because our calendar does not have the same number of days in each month, and partly because the orbit is elliptical, not circular, and the Earth travels at a different rate at different times of the year. However, the difference is never more than a day or two. The length of the hours of daylight at any particular latitude varies with the declination of the sun. The rate of change of the length of daylight will therefore be greatest when the rate of change of declination is greatest. You can see that between about the 7th of March and the 7th of April, the declination changes by 20 degrees. A similar situation occurs around September the 21st. Therefore, the rate change of the length of daylight will be greatest at the spring and autumn equinoxes. At the summer and winter solstices, not only is it the flattest part of the curve, but it is also changing direction. There is hardly any change in declination, and therefore very little change in the length of the hours of daylight. This explains the origin of the words solstice and equinox. Solstice comes from two Latin words, sol and sticere, which means sun and to stand still. To the ancients, it seemed that the sun was standing still at midsummer and midwinter, because at those times of the year the days did not appear to change length. The word equinox comes from two Latin words meaning equal night, because at the spring and autumn equinoxes we get closest to 12 hours of daylight and 12 hours of darkness. Just as declination is the celestial equivalent of latitude, we also need a celestial equivalent of longitude in order to define the position of a body in 2 dimensions. This is called hour angle, and it is defined as the arc of the equinoctial between a datum meridian and the meridian of a celestial body. It is similar to longitude, except that it is always measured westwards. Let's look down on the Earth from above the North Pole. We choose a datum meridian. As the sun or star transits the datum meridian, the hour angle is 0. In this example, another celestial body is 80 degrees west of the datum, so its hour angle is 080. Here we see the Greenwich meridian being used as the datum. Position 3 has a Greenwich hour angle of 050, which corresponds to longitude 50 west. Position 4 has a Greenwich hour angle of 180, which corresponds to the Greenwich anti-meridian. And position 5 has a Greenwich hour angle of 270, which corresponds to longitude 90 east. Note that it is not necessary to say 270 west. It is always west. If the hour angle is measured from the observer's meridian, it is called the local hour angle and abbreviated to LHA. If measured from the Greenwich meridian, it is called the Greenwich hour angle and abbreviated to GHA. Because the Earth is rotating, the hour angle is constantly changing and is only valid at a specific time. By contrast, declinations of stars are constant for many years. Even the sun's declination can be regarded as constant over a period of a day. Let's summarize this lesson. The Earth's orbit is almost circular, so the difference in distance at summer and winter has very little effect on the climate. The plane of the orbit of the Earth round the Sun is called the ecliptic. However, the Earth's spin axis is at an angle of 66.5 degrees from its ecliptic. The plane of the Earth's equator extended out into space is called the equinoctial. The angle between the equinoctial and the ecliptic is therefore 23.5 degrees. The Earth's orientation in space does not change significantly and can be taken as constant over a period as short as 1 year. What does change, however, is its orientation relative to the Sun. Declination is the celestial equivalent of latitude. Seen from an Earth-centered point of view, the Sun's declination appears to change like this over the year. This annual change of the Sun's declination explains the seasonal variations in temperature. It also defines the Tropic of Cancer at 23.5 degrees north and the Tropic of Capricorn at 23.5 degrees south. They are the highest latitudes that the Sun can ever be directly overhead. The annual change of declination also explains the variation in the hours of daylight at different latitudes throughout the year. This gives us the definition of the Arctic and Antarctic circles, at 66.5 degrees north and south. They are the lowest latitudes at which it is possible to have at least 1 day a year of continuous daylight or continuous darkness. The graph of declination is very close to a sine wave. It gives the most rapid changes in the length of the hours of daylight at the spring and autumn equinoxes, in March and September. The longest and shortest days occur at the summer and winter solstices. Just as declination is the celestial equivalent of latitude, our angle is the celestial equivalent of longitude, in order to define the position of a body in 2 dimensions. It is always measured westwards. If the hour angle is measured from the observer's meridian, it is called the local hour angle, and abbreviated to LHA. If measured from the Greenwich meridian, it is called the Greenwich hour angle, and abbreviated to GHA. Declinations change relatively slowly, but hour angles change continuously as the Earth rotates, and must be referred to a specific time. This completes the second lesson on time. The next will look at the various forms of time used in order to cater for longitudes other than Greenwich. This is the third of our lessons on time. In it, we look at the various forms of time used in order to cater for longitudes other than Greenwich. As we said earlier, by using an apparent solar day, we have a civil day which is of a constant length of 24 hours, with midday occurring approximately at meridian transit. The Earth therefore rotates one full rotation of 360 degrees with respect to the mean Sun in 24 hours. This is equivalent to rotation of 15 degrees of longitude in 1 hour, or 1 degree of longitude in 4 minutes, or 15 minutes of longitude in 1 minute of time. Local mean time, or LMT, is the time as determined by the mean Sun at an observer's local meridian. The datum for measuring the local time is the local noon, which occurs when the mean Sun is transiting that particular meridian. Here, as an example, the time at longitude 45 east is 1200 hours. Therefore, at 15 degrees an hour, the Earth will have to rotate for another 3 hours until the Greenwich meridian experiences noon. So the LMT at Greenwich must be 9 a.m. And similarly, longitude 90 east, which is 45 degrees further eastward, must have experienced noon 3 hours ago. Therefore its LMT must be 3 o'clock in the afternoon, or 1500 hours. We can therefore convert LMT at one longitude to LMT at another simply by the longitude to time conversion of 15 degrees per hour. Here we see local mean times at various longitudes going eastwards, as far as the Greenwich antimeridian. We'll assume that the date at 45 east is the 16th of May. The Earth is at the centre of the diagram. As the scene is Earth-centred, instead of the Earth spinning eastwards, we imagine the Sun moving westwards.
At 90 east, the LMT is 1500 hours. The Sun passed over it 3 hours ago. At 135 east, it is 1800 hours. The Sun passed over it 6 hours ago. And at the Greenwich anti-meridian, 180 degrees east, the LMT is 2100 hours, still on the 16th of May. Now let's look at the same situation, this time going westwards. The mean Sun will not be overhead for another 3 hours. It must be 0900 hours LMT. But as we said last lesson, the local mean time at Greenwich is the definition of Greenwich Mean Time. So the GMT is also 0900 hours. We now use UTC, which for all practical purposes is the same thing. Continuing westwards, the Sun will not pass over 45 west for another 6 hours, because the change of longitude is 90 degrees. It must therefore be 0600 hours local mean time. And so on, until we get to longitude 135 west. This is 180 degrees west of 45 east, and so the time is 12 hours earlier, which is 0000 hours on the 16th of May, or, if you prefer, 2400 hours on the 15th. If we go a further 45 degrees westwards to the Greenwich anti-meridian, we are 3 hours earlier. This takes us to 2100 hours on the 15th of May. But if you remember, it was also 2100 hours on the 16th of May when we counted it forwards, going eastwards. Therefore, local mean time changes date when crossing the Greenwich anti-meridian. This is similar to the international date line, which follows the 180-degree meridian for the most part, with a few deviations. However, for LMT calculations, these deviations do not apply. Date changeover always occurs at the 180-degree meridian. The time on both sides of the meridian is 2100 LMT, but the date to the west is 15th of May and to the east is 16th of May. From the calculations we have just done, we can deduce the rule that applies when crossing the international date line. When crossing from west to east, add 1 day. And when crossing from east to west, subtract 1 day. Local mean time is not used for timekeeping and does not relate to anything we set on a watch because it changes as soon as we change our longitude. However, it is important because we use it as part of the calculation of the time of astronomical phenomena, in particular sunrise, sunset, and twilight. We therefore need to know how to convert from LMT at one longitude to LMT at another, and how to convert between LMT and UTC. There are 2 methods, which are the tables in the Air Almanac and direct division of longitude. We'll start with the use of the tables. The first 2 columns are headed degrees and hours and minutes. Let's go to 15 degrees. The time beside it is 1 hour and 0 minutes. Now look at 16 degrees. This is 1 hour and 4 minutes. The first 2 columns go from 0 to 59 degrees. The rest, up to the grey dividing column, cover the remaining whole degrees up to 359. The columns to the right of the vertical divider are headed minutes of longitude and minutes and seconds of time. We know that 1 degree of longitude is 4 minutes. So if you look up 30 seconds of longitude, this corresponds to a time of 2 minutes and no seconds. Let's now do a practical example. We'll convert 137 degrees and 36 minutes of longitude to a difference in local mean time. Start with 137 degrees.
What does this equate to? (137° converts to 9 hours and 8 minutes of time. Now look up the 36 minutes. What does this equate to? (36 minutes of arc converts to 2 minutes and 24 seconds of time. Adding them together gives you 9 hours, 10 minutes and 24 seconds. In fact, for our purposes, the nearest minute is close enough. The second method is by simple division of the angle by 15, but it is easier if you use a scientific calculator with a degrees, minutes, seconds or DMS facility. The actual buttons to be pressed depend on which particular calculator you have bought. On this example, the DMS button looks like this. You start by entering the degrees. Press 137. Then press the DMS button. This little square appears. Then enter the minutes. Press 36 and then the DMS button. Finally, press divide 15 equals. This is a good deal quicker and easier than the tables, and it means that you can still solve these conversions even if the tables are not included as part of the exam. Now we'll look at some practical examples. We'll find the LMT at longitude 103 degrees and 55 minutes east, which is in Singapore if the UTC is 0800 hours. Your first step is to convert 103 degrees and 55 minutes of longitude to time difference. Work it out by one of the methods shown in the last scene. You should have got the answer 6 hours, 55 minutes and 40 seconds. We'll call that 6 hours and 56 minutes. The next question is the LMT going to be an earlier or later time than UTC? Look at the diagram. The Earth is spinning eastwards. Does Singapore transit the Sun before or after Greenwich? The answer is obviously before. So the time in Singapore will be later. 0800 hours plus 6 hours 56 minutes gives us a local mean time of 14:56. Note that in the table we have a column for the date, as well as hours and minutes. We do not need to use it for this calculation, but get used to putting it in as a matter of habit, because it is sometimes essential. When working out whether LMT is earlier or later than UTC, you can use the rule longitude west, UTC best, longitude east, UTC least. Another useful rule is that when they're having breakfast in New York, it's lunchtime in London and tea in India. Now we'll do an example of the change of LMT from one longitude to another. In this one, you will see why it is important to have a column for the date. The local mean time at A, longitude 137 degrees and 50 minutes west, is 1812 on the 18th of August. What is the LMT at B, longitude 121 degrees and 12 minutes east? Always lay the problem out in a table and always work through UTC. The first thing to do is to calculate the longitude to time conversion. This is sometimes referred to as the arc to time conversion. You can then work out whether you need to add or subtract to arrive at UTC. When you've done that,
click to continue. You should have got that you need to add 9 hours and 11 minutes. This gives you a UTC of 3:23 on the 19th. You can now see why we need the date column. We now need to convert from UTC to LMT at B, which has a longitude of 121 degrees and 12 minutes east. Again, do the calculation and work out whether you need to add or subtract to arrive at LMT for an easterly longitude. When you've done that, click to continue. You should have got that you need to add 8 hours and 5 minutes. This gives a local mean time at B of 11:28 on the 19th. Now, you may have noticed that this question could have been solved without working through UTC. The total change of longitude from A to B is 259 degrees and 2 minutes, which converts to 17 hours and 16 minutes later than A's LMT. Working through UTC as we did may seem longer, but it is very easy to make a mistake if you take shortcuts, especially if the date changes. Always use a tabular layout and work through UTC. However, LMT is unsuitable for keeping on our watches because it varies, as we have said, with change of longitude. Take the United Kingdom for instance. Suppose that the mean sun is passing over the Greenwich meridian, so that the LMT there is 12 noon. This means that it was over Great Yarmouth 7 minutes ago. Its LMT is 12:07. However, the mean sun will not pass over Oxford for another 5 minutes. This makes the LMT at Oxford 11:55. It will not pass over Swansea, which is at 4 west, for another 16 minutes. This makes the LMT at Swansea 11:44. And similarly, we can work out local mean times at Land's End and Londonderry. So, between Great Yarmouth and Londonderry, the LMT is 35 minutes different. We cannot work like this when we have train, coach and airport connections to make. We need a standard time for the whole of the country. For the UK, that standard time is UTC in winter and UTC +1 in summer. Most other countries keep different standard times, and we shall look at that now. Standard time is defined as the official time in a local region adjusted for location round the Earth, established by law or custom. It is up to the government of each country to decide what time difference from UTC to keep. Many world atlases include a map of world standard times, often incorrectly called time zones. A typical example is shown on the screen. Previously, we have considered that the maximum time difference from GMT or UTC is 12 hours. For administrative reasons, some of the groups of islands have chosen a standard time that crosses the 180-degree meridian, resulting in a time difference of 13 hours. This causes the international dateline to deviate from the Greenwich anti-meridian. You can also see that countries with a large longitudinal extent have no option but to subdivide into regions, each with its own standard time. Typical examples are North America and Russia. The Air Almanac contains 3 lists of countries showing their standard times. List 1 tabulates those countries which are mainly to the east of the Greenwich meridian, and are therefore ahead of UTC. The figures shown should be added to UTC to give standard time and subtracted from standard time to give UTC. This applies to the other tables also. Some large countries are divided into areas having different standard times. For example, Australia. Some countries operate daylight saving time during the summer months. This is indicated by an asterisk alongside the country name. Note that in all cases, daylight saving time is the addition of 1 hour to the standard time during summer months, normally between April and October. List 2 at the top of page 3 shows those countries that keep UTC. This is followed by List 3, which shows those countries, mainly west of Greenwich, which are slow on UTC. We will start with a simple conversion of standard time to LMT. Given the standard time in Nairobi, Kenya, is 15:32 on 10th of June, calculate the LMT in Madrid, Spain. The exact coordinates are shown in the text box. As before, use a tabular layout and always work through UTC. From List 1 of standard times in the Air Almanac, we see that Kenya is 3 hours ahead of UTC. Therefore, the UTC is 12:32 on the 10th of June. The longitude of Madrid is 3 degrees 42 minutes west. So, to convert the UTC just calculated to LMT, we need to use our calculator or go to the Arc to Time page in the Air Almanac. Round the answer to the nearest whole minute. Madrid is west of Greenwich, so GMT is best. Therefore, LMT Madrid is 12:32 minus 15 minutes, which is 12:17 LMT on the 10th of June. Standard time is appropriate for land. What about ships at sea? We'll finish by looking at zone time. At sea, in order to keep the ship's time related to day and night, the clocks are altered by 1 hour for each 15 degrees of longitude change of position. The datum used is the Greenwich meridian, as shown on the screen. The band of longitude, 7.5 degrees either side of the datum, uses UTC as the zone time. From 7.5 degrees east to 22.5 degrees east, the zone time is 1 hour ahead of UTC. From 22.5 degrees east to 37.5 degrees east, the zone time is UTC plus 2 hours, and so on. This division of longitude continues through to 180 degrees. Note that the numerical values for easterly longitudes are negative, as this is the correction to be applied to the zone time in order to calculate UTC. Similarly, westerly zone time values are positive, since the time west of Greenwich is behind UTC. The zones are also given letters, as shown with the UTC zone being Z or Zulu. Thus 1200 GMT is also 1200 Zulu. When approaching 180 degrees longitude in the Eastern Hemisphere, between 172.5 degrees east to 180 degrees, the time difference is shown as minus 12 hours. Whereas from 172.5 degrees west to 180 degrees, the time difference is shown as plus 12 hours. Therefore, as we saw in the lesson on LMT, when travelling from east to west across the 180-degree meridian, subtract 1 day. And when travelling from west to east, add 1 day. Although zone time is used only at sea, the term Zulu time to mean UTC is also used by military forces and by many aviators.
Let's summarize this lesson. Local mean time, or LMT, is the time, as determined by the mean sun, at an observer's local meridian. The datum for measuring the local time is the local noon, which occurs when the mean sun is transiting that particular meridian. It is important because we use it as part of the calculation of the times of sunrise, sunset, and twilight. We can solve longitude to time conversions using either the tables or a calculator. This is known as arc to time conversion. When carrying out these conversions, always lay out the working in a table and work through UTC. However, LMT is unsuitable for keeping on our watches because it varies with change of longitude. We therefore keep standard time. Standard time is defined as the official time in a local region, adjusted for location round the Earth, established by law or custom. It is up to the government of each country to decide what time difference from UTC to keep. You must be familiar with the operation of the tables and be able to convert between LMT, UTC and standard time in different countries. The international date line does not always follow the 180-degree longitude line. But if you look up the information from the tables and follow the tabular layout, date changes look after themselves. Finally, there is zone time, which is kept at sea. It has little practical relevance to aviators, but the term Zulu time, meaning UTC, is widely used. This concludes this lesson on time. The next will cover sunrise and sunset. This is the last of 4 lessons on time. In it, we shall learn how to calculate the times of sunrise, sunset and twilight, and to understand their significance in flying operations. In an earlier lesson, we showed that it was the annual change of declination which causes the seasonal variation in the length of the hours of daylight. Here is the Earth on June the 21st. We'll take 2 positions on the Greenwich meridian, both experiencing local noon. One is at the equator, and the other at 40 north. The Earth now rotates for 6 hours, so that the local time for each of them is 6 p.m. You can see that the position at the equator is passing into darkness. However, the position at 40 north is still in daylight because of the inclination of the Earth. The Earth will have to rotate for another 1.5 hours before this point passes into darkness, when the local time is 7:30 in the evening. This is a Northern Hemisphere summer, when the daylight hours are longer. However, for the Southern Hemisphere, it is winter. Their daylight hours are shorter. Here, the Earth has to rotate until only just after 4:30 in the evening for it to pass into darkness. 6 months later, the situation is reversed. You can see that the hours of daylight are now longer in the Southern Hemisphere. For them, it is summer, whilst the Northern Hemisphere has its winter. The references used to define sunrise and sunset do not result in exactly 12 hours of daylight and 12 hours of darkness, even at the 2 equinoxes. Let's see why. The first reason is that we do not take the center point of the sun as our datum. The point in time used to define sunrise is when the top tip of the sun first appears. Similarly, the point in time used to define sunset is when the top edge of the sun finally disappears below the horizon. The combination of the size of the sun and its distance from us results in its diameter having an angular arc of 32 minutes. This means that its radius subtends an angle of 16 minutes. Astronomers usually call this the semi-diameter, not the radius. However, we also have to consider atmospheric refraction. This is a diagram of the Earth as seen from above. We are looking down on the North Pole. If atmospheric refraction did not exist, then we would have half the Earth in light and half in darkness. But in practice, we have an atmosphere which bends light round the surface at the edges. The amount of atmospheric refraction at sunrise and sunset is 34 minutes of arc. For an observer at position Q, the tangent to the Earth's surface is the straight line that would be defined in space by a spirit level. This is called the sensible horizon. The horizon that is actually seen because of atmospheric refraction is called the visual horizon. This is 34 minutes below the sensible horizon. However, at the moment of sunrise or sunset, the centre of the Sun is another 16 minutes below the visual horizon. So, at the defined time of sunrise or sunset, the Sun is a total of 50 minutes of arc below the sensible horizon. This is the figure that is used in the air almanac tables. It always makes at least 3 minutes difference in time at both ends of the day. This means that even at the equinoxes, the time between sunrise and sunset at the surface of the Earth is 12 hours and 6 minutes, and the time when the Sun is below the horizon is 11 hours and 54 minutes. The entering arguments for sunrise, sunset and twilight are latitude and declination. However, the Air Almanac has converted the declination into date for you. The listed times are tabulated for every third day. If you need an intermediate day, you have to interpolate. Between the equator and 30 north or south, the latitudes are given at 10-degree intervals. Between 30 and 50, they are listed for every 5 degrees. And above 50, they are for every 2 degrees. Again, you have to interpolate if required. So let's look up the time of sunset at 52 south, 22 west on the 19th of April. Go along the 52 south row until you find or straddle the date. In this case, it is between the 17th and the 20th. So what does that give us for the 19th? Click to continue when you've got the answer. Interpolating gives us 1706 LMT. Remember, all these sunrise, sunset and twilight times are LMT. However, LMT is no use to us for timekeeping. To relate it to time on our watch, we need to convert it to UTC. The longitude was 22 west. So what is the UTC time of sunset? Again, click to continue when you've got the answer. You should have come up with 1834 UTC. As the sun sets, the Earth is not plunged into instant darkness. Similarly, there is a period of dawn before sunrise. The atmosphere scatters the sun's light, and so around sunset and sunrise there is a period of partial light known as twilight. This is divided into 3 shorter phases, based on the depression angle of the Sun below the sensible horizon. Evening civil twilight occurs between sunset and when the centre of the Sun is 6 degrees below the sensible horizon. Morning civil twilight occurs when the centre of the sun is 6 degrees below the sensible horizon and sunrise. During civil twilight, tasks can be undertaken without the use of artificial light. For our purposes, this means that you can land and take off at an airfield without lighting up to the end of evening civil twilight and after the beginning of morning civil twilight. Nautical twilight occurs when the centre of the sun is between 6 and 12 degrees below the sensible horizon. During this time, the major navigation stars and planets are visible, and it is still possible to use the horizon as a reference. Astronomical twilight occurs when the centre of the sun is between 12 and 18 degrees below the sensible horizon. For practical purposes, this can be considered as darkness. As aviators, we are only concerned with civil twilight. Night flying starts at the end of evening civil twilight and ends at the beginning of morning civil twilight. The length of twilight depends on the observer's latitude and the time of the year. This is the situation at the equator at an equinox. Here is the point of sunset, 50 minutes below the sensible horizon. Here is the end of evening civil twilight, 6 degrees below the sensible horizon. This gives a zone of 5 degrees and 10 minutes of arc for the period of twilight. The Earth rotates at 15 degrees an hour, so the shortest possible duration of twilight is 21 minutes. This is the situation as seen by an observer on Earth at the equator at an equinox. However, at some other time of the year, such as the solstice shown here, the effect of the declination is that the Earth takes longer to rotate through the twilight zone. And at a higher latitude, although the Earth distance through the twilight zone is the same, the change of longitude is greater because of Earth convergence. Twilight therefore lasts longer. Here are these situations, as seen by an observer on Earth in these cases. The slanting one is how it appears to an observer whose latitude is north of the sun's declination. You can see that the period is longer than 21 minutes. For example, the duration of civil twilight in the UK in midsummer is about an hour. And this is how it appears to an observer whose latitude is south of the sun's declination. Again, you can see that the period is longer than 21 minutes. The times for the start of morning civil twilight and the end of evening civil twilight are found in the Air Almanac, in the same format as for sunrise and sunset. The duration of civil twilight can be calculated from the difference found in the sunrise or sunset tables and the twilight tables. For example, sunrise at 50 north on the 14th of January is at 07:54 LMT. Morning civil twilight begins at 07:17 LMT. Therefore, the duration of civil twilight is 37 minutes. We showed in an earlier lesson that at latitudes above the Arctic and Antarctic circles, it was possible to have continuous daylight or continuous darkness at certain times of the year. These symbols are used in the Air Almanac to indicate these phenomena. Let's look at what they mean. The first indicates that the sun remains continuously above the horizon. This occurs at a high latitude summer. The path of the sun is like this. It comes down and up in the usual way, but at its lowest point, which is at midnight, it is still above the horizon. There is no sunset or sunrise. The second symbol means that the sun remains continuously below the horizon. This occurs at a high latitude winter. The sun comes up and down in the usual way, but at its highest point, which is at midday, it is still below the horizon. There is no sunrise or sunset. And the final symbol means that in the period between sunset and sunrise, the sun is never less than 6 degrees below the sensible horizon. This occurs during a high-latitude summer. The sun sets, but at its lowest point, at midnight, it has not reached 6 degrees below the horizon. We still get a sunset and sunrise, but twilight lasts all night. The sunrise, sunset and twilight tables are based on an observer at mean sea level on flat ground or looking out to sea. An increase in altitude will increase the sensible horizon, thus making sunset later and sunrise earlier. It also makes twilight shorter. However, you will not be required to calculate any of this. A further variable to the length of twilight is caused by volcanic activity. In an area of volcanic eruption, the length of twilight will be increased due to the increased scattering of the sun's rays. In practice, you are unlikely to be flying in such conditions. Finally, you should note that the beginning and end of civil twilight are the practical basis for working out when it gets too dark to see safely, and can be used worldwide. However, within the UK, the Air Navigation Order states that for legal purposes, such as logbook entries, night flying takes place 30 minutes after sunset until 30 minutes before sunrise. Let's summarize this lesson. We showed that the times of sunrise and sunset are determined by latitude and the sun's declination. At the defined time of sunrise or sunset, the sun is a total of 50 minutes below the sensible horizon. This is the figure that is used in the air almanac tables. It always makes at least 3 minutes difference at both ends of the day. We saw how to look up the times of sunrise in the air almanac. But these are local mean times. To make them useful to us, we have to convert to UTC, and then possibly to standard time if required. However, before sunrise and after sunset, there is a period when it is still light enough for everyday tasks, including landing and taking off from an airfield without lighting. This period is known as civil twilight. There are also periods of nautical twilight and astronomical twilight, but these need not concern us as aviators. The local mean times of the beginning of morning civil twilight and the end of evening civil twilight are given in the air almanac in the same format as the sunrise and sunset tables. Again, they need to be converted to UTC to be useful. To find the duration of twilight, compare its time with that of sunrise or sunset as appropriate. Twilight can never be shorter than 21 minutes, which occurs at the equator at an equinox. Remember the significance of the 3 symbols used in the air almanac to cover high-latitude special cases. An increase in altitude will increase the sensible horizon, thus making sunset later and sunrise earlier. It also makes twilight shorter. Finally, within the UK, the Air Navigation Order states that for legal purposes, such as logbook entries, night flying takes place 30 minutes after sunset until 30 minutes before sunrise. This concludes all of the lessons on time. We are now going to study one of the most important safety considerations in long-haul flying. It is known as point of equal time. This is often abbreviated
to PET. It is also called equal time point, which can be abbreviated to ETP. An older name for it is critical point. If you see any of these terms or abbreviations, they all mean the same thing. The majority of transport flights take place over routes where there are many en route alternate aerodromes. In the event of an emergency requiring an in-flight diversion, there are usually several available. However, over some routes, there may be no diversion available over a large part of the flight. Oceanic transits, such as this one over the Atlantic, are one example. After passing Gander, which is the most easterly point of Canada, the next available airfield is Shannon in Ireland. This is a distance of over 1,700 nautical miles. Should a failure occur at some point over the Atlantic Ocean, the most important consideration is to get the aircraft on the ground as soon as possible. This is a point of equal time problem. The point of equal time is defined as that point along track from which it will take the same time to fly to one of two airfields. Therefore, if an emergency takes place after the PET, it is quicker to go on. And if before the PET, it is quicker to return. The point of equal time therefore occurs when time on equals time home. The determination of the PET is a time problem, and there will always be sufficient planned fuel for the aircraft to fly to one of the nominated airfields. The amount of fuel carried is not a consideration. Point of equal time may be calculated between the departure and destination airfields, as in this example, or it may be calculated for that part of the route for which no diversion airfield exists. Let's look at a practical example and see what factors determine point of equal time. Let's assume a route 400 nautical miles long with no diversion between the start and finish airfields. Let's assume that the aircraft has a constant TAS of 200 knots and that there is no wind. In that case, the calculation is a simple one. The point of equal time is also the point of equal distance. It occurs halfway along the route. We do not take the time to turn into consideration. Turning through 180 degrees at rate 1, 3 degrees a second, takes only 1 minute. This is negligible compared with the total flight time. If we continue onwards, we will have 200 nautical miles to cover at a ground speed of 200 knots. But also, if we come home, we will also have 200 nautical miles to cover at a ground speed of 200 knots. Now, we'll leave the halfway mark on the diagram, just for reference. But we'll look at the effect of a 50-knot headwind all the way along the route. Now the ground speed onwards will be 150 knots, while the ground speed home is 250. The point of equal time has now moved forwards to a distance of 250 miles from the departure point. The distance onwards will be 150 miles at 150 knots, and the distance home will be 250 miles at 250 knots. The effect of the headwind has therefore been to move the point of equal time towards the direction that the wind is coming from. What if it had been a tailwind? Let's now imagine that we're flying over the same route on a different day, and this time the mean wind over the whole route is a tail component of 30 knots. In this case, the ground speed onwards will be 230 knots, whilst the ground speed home is 170. The point of equal time moves backwards to a distance of 170 miles from the departure point. The distance onwards will be 230 miles at 230 knots, and the distance home will be 170 miles at 170 knots. The effect of the tailwind has also been to move the point of equal time towards the direction that the wind is coming from. So the effect of any wind component along track, whether head or tail, is always to move the point of equal time towards the direction that the wind is coming from. Let's now derive the formula to calculate point of equal time in general terms using algebra. We'll call the distance between our two diversion airfields d. Somewhere along the route is the point of equal time. We don't know where it is yet. This is what the equation is going to find out for us. So it's an unknown distance, x. We'll call the onward ground speed from the point of equal time o, and the homebound ground speed h. The basic definition of point of equal time means that the time onwards must be the same as the time home. But time is distance divided by ground speed. For example, if you have 100 miles to drive and your speed is 50 miles an hour, it would take you 2 hours. The distance home is x, and the ground speed home is h. If the total distance is d, and the distance home from the PET is x, then the remaining distance onwards from the PET must be d minus x. And the ground speed onwards is o. We are trying to find x, so we need to isolate it on one side of the equation. We start by cross-multiplying. This gives us xo equals h, open brackets, d minus x, close brackets. Multiplying out, we get xo equals dh minus xh. We now need to get the term xh onto the left-hand side of the equation. So we bring it across, changing the sign as we do so. This gives us xo plus xh equals dh. Factorise the left-hand side to isolate x. And now divide both sides by o plus h. This gives the final equation x equals dh over o plus h. This is the one that you must remember. You will not be examined on the derivation which we have just shown. We put it in to demonstrate that the equation is based on good logical algebra and is correct. But whether you remember that part or not, you must be able to recall the result, which is that x equals dh over o plus h. This is the starting point for all point of equal time questions. We'll now try some simple worked examples using the formula, and demonstrate that the algebra gives the same results as our earlier basic navigation calculations. Assume a total distance of 500 nautical miles and a true airspeed of 300 knots. Let's start off with the still air case. In this situation, O, the onward ground speed, is 300 knots. And H, the homebound ground speed, is also 300 knots. Let's write the formula down. X equals dH over O plus H. D is 500, and O and H are both 300. So X, the distance to the point of equal time, is 500 times 300 over 600, which comes to 250 nautical miles. This is halfway, which was exactly what we found when we did a still air example earlier. Now let's see what the effect of 60 knots headwind will be. Again, the total distance is 500 nautical miles, and the true airspeed is 300 knots. However, this time we have 60 knots headwind. Now O, the onward ground speed, will be the combination of the 300 knots TAS and the 60 knots headwind. This gives an onwards ground speed of 240 knots. However, if we return, the headwind becomes a tailwind, and H, the homebound ground speed, becomes 360 knots. Here's the formula. X equals DH over O plus H. D is 500, and O is 240, and H is 360. This means that x, the distance to the point of equal time, is now 500 times 360 over 600, which comes to 300 nautical miles. So using the algebra confirms what we have shown with simple navigation calculations earlier. The effect of a wind component along track is to move the point of equal time towards the direction that the wind is coming from. Now let's consider 60 knots tailwind. This time O, the outbound ground speed, will be the combination of the 300 knots TAS and the 60 knots tailwind. This gives an onwards ground speed of 360 knots. However, if we return, the tailwind becomes a headwind, and H, the homebound ground speed, becomes 240 knots. Here's the formula again. X equals DH over O plus H. D is 500, and O is 360, and H is 240. This means that X now becomes 500 times 240 over 600, which comes to 200 nautical miles. And again, using the algebra confirms what we had shown with simple navigation calculations earlier. The effect of a wind component along track is to move the point of equal time towards the direction that the wind is coming from. So let's summarize this lesson. The point of equal time is defined as that point along track from which it will take the same time to fly to one of two airfields. It is calculated from a simple formula, which must be learnt. D is the distance between the two airfields being considered. X is the distance from the start to the point of equal time. The onward ground speed from the point of equal time is called O, and the homebound ground speed is called H. The effect of any wind component along track is always to move the point of equal time towards the direction that the wind is coming from. This is true whether it is a headwind or a tailwind. Recapping our previous work, there are situations when there may be no diversion available for a large part of the flight. Oceanic transits, such as this one over the Atlantic, are one example. The point of equal time is defined as that point along track from which it will take the same time to fly to one of two airfields. If an emergency were to occur after the PET, it would be quicker to go on. And if before the PET, it is quicker to return. The point of equal time therefore occurs when time on equals time home. It is affected by wind component along track, so will vary from flight to flight, even along the same route. It can be found from the formula that x equals
d times h over O plus h. This is the starting point for all point of equal time questions. Up until now, we have assumed that the wind component remains constant all the way along the route. For instance, in this example, we had a total distance of 500 nautical miles and a true airspeed of 300 knots. The wind component was 60 knots head. This was valid for the whole of the route. This made O, the onward ground speed, 240 knots. And H, the homebound ground speed, was 360 knots. We substituted into the equation x equals d times h over O plus h and calculated x to be 300 nautical miles. This gave us a distance of 300 nautical miles from the departure airfield to the point of equal time. However, this idea of a constant wind component all the way along the route does not always reflect reality. Over a long track, such as the North Atlantic, the wind may well change, particularly if the route crosses a weather front. We're going to show this in the following scenario. We have a route distance of 2,050 nautical miles, from last point of diversion A to next available diversion B. The aircraft's true airspeed is 475 knots. When we start off, the wind component is 45 knots tail. We're going to assume that the wind changes approximately halfway along the route, close to where the point of equal time occurs. Clearly, this is something of an assumption, because the wind itself affects the position of the point of equal time. However, wind forecasting is not always a precise science, and this supposition is going to be near enough for practical purposes. From the point of equal time onwards, the wind component is assumed to be 10 knots head. This means that O, the onwards ground speed, is 465 knots, and H, the homewards ground speed, is 430 knots. Now we substitute into our usual equation x equals d times h over O plus h. D is 2,050, O is 465 knots, and H is 430 knots. If you get your calculator out and do the maths, you will find that the distance to the point of equal time is 985 nautical miles. Just so that you get used to the terminology, we'll use the term critical point for the point of equal time from now on. It's almost as common, and you should be familiar with it. We now need to work out the time to the critical point. This is an important piece of information, as we shall shortly show. The first thing to notice is that the ground speed to the critical point is not O if the wind changes. O assumes a headwind component of 10 knots. But out to the critical point, the wind component is 45 knots tail. Therefore, a TAS of 475 knots plus a tailwind of 45 knots gives a ground speed out to the critical point of 520 knots. So our time to the critical point is 985 nautical miles at a ground speed of 520 knots, which comes to 113.5 minutes. Let's check the algebra out now. If the distance to the critical point is 985 nautical miles, and the total distance d is 2,050, simple subtraction tells us that d minus x, the distance onwards from the critical point, is 1,065 nautical miles. If you get your calculator or nav computer out, you find that the time onwards, that is 1,065 nautical miles at 465 knots, comes to 137.5 minutes. And the time home is 985 nautical miles
at a ground speed of 430 knots, which also comes out to 137.5 minutes. There are some emergencies that require a landing as soon as possible, but do not involve a change of true airspeed. A sick passenger or perhaps a generator failure might be examples. However, in many instances, an onboard emergency will involve a loss of altitude. For example, an engine failure will result in a drift down to a stabilizing altitude, and a pressurization failure would require an immediate descent to 10,000 feet. This will almost invariably involve a loss of TAS. We are now going to assume that flight at a lower altitude following an emergency has reduced our TAS to 380 knots. This will affect our ground speeds. O, the onwards ground speed, is now 370 knots. And H, the homewards ground speed, is now 335 knots. As always, X equals D times H over O plus H. D is 2050. O is 370 knots. And H is 335 knots. Again, get your calculator out and do the maths. The distance to the critical point is now 974 nautical miles. Now let's see what the new time to the critical point is. There is an important point for you to understand here. Even though we are dealing with a one-engine-out critical point, we still use the all-engine TAS to find the time to it. If an emergency necessitating a reduced TAS were to occur before the critical point, it would be unthinkable to continue onwards to it. You would go back. You don't need to know the one-engine-out time to the critical point. You would never use it. Emergencies do not occur on the vast majority of flights. They proceed without incident. However, when we are flying on a normal, all-engines routine flight, we still want to know whether we have reached the one-engine-out critical point yet, in order to allow us to make a decision where to go if we should lose an engine. We therefore calculate the time to the one-engine-out critical point at the all-engines speed. As before, a TAS of 475 knots, plus a tailwind of 45 knots, gives a ground speed out to the critical point of 520 knots. This time, our time to the critical point is 974 nautical miles, at a ground speed of 520 knots, which comes to 112.5 minutes. Let's compare the answers we got for the all-engines critical point and the one-engine-out critical point. Using the all-engines TAS after the critical point, the distance to the critical point was 985 nautical miles, and the time was 113.5 minutes. Using the one-engine-out TAS after the critical point, the distance to the critical point was 974 nautical miles, and the time was 112.5 minutes. At first sight, this seems like a pretty remarkable result. The TAS from the critical point has reduced from 475 knots to 380. That's very nearly 100 knots. And yet the position of the critical point has moved by only 11 miles over a route distance of 2,000 miles. Why is this? Think about it for a while and try to come up with your own answer before you click to continue. The reason that we get such a small shift in the position of the critical point, even though the TAS has changed by nearly 100 knots, is that the position of the critical point depends on the ratio of O to H. If the wind component is not very strong in comparison to the true airspeeds involved, that ratio does not change much. The ground speeds change significantly, but their ratio to each other does not. In this example, O included 10 knots headwind, and H included 45 knots headwind. That is a difference of only 35 knots headwind. Whether the TAS is 475 knots or 380 does not make a lot of difference to the ratio of the ground speeds. Now, the idea of the critical point is that it is pre-calculated as part of the flight planning process. Then, as the aircraft passes over the last point of diversion before the oceanic leg, the actual time of arrival is noted. The pre-planned time to the critical point is extracted from the flight plan and added to the actual time of arrival over the last waypoint. This takes all the decision-making out of in-flight emergencies. If one should occur, there is no frantic searching through charts or rapid calculation in the air. The decision is a simple one. If the time is less than 112.5 minutes after the last waypoint, we turn back. If it is more, we go on. We do not want to complicate this decision by having different critical points for different situations with different ETAs. Because the difference between the 2 points is usually quite small, we always take the one engine out situation. This covers the worst case, so this is the calculation we use. The all engines time to the critical point is usually very similar whether we take the all engines or the one engine out point. However, if we use the reduced TAS after the critical point, the time to the alternate airfield will obviously increase. The distance to the one engine out critical point X was 974 nautical miles. With a total distance D of 2,050 nautical miles, the distance onwards from the one engine out critical point is 1,076 nautical miles. O, the reduced ground speed onwards, is 370 knots. And H, the reduced ground speed home, is 335 knots. As before, if you get your calculator or nav computer out, you find that the time onwards, that is, 1,076 nautical miles at 370 knots, comes to 174.5 minutes. And the time home is 974 nautical miles at a ground speed of 335 knots, which also comes to 174.5 minutes. The time we calculated using the all-engine speeds after the critical point was 137.5 minutes. This is shorter by 37 minutes. Sometimes you are given wind velocity and track instead of component, and you have to calculate O and H yourself. Here is an example. The track between A and B is 030 degrees true, and the distance is 500 nautical miles. The aircraft has a true airspeed of 180 knots. The forecast wind all the way along the route is 35 knots from 090 true. What is the distance and time to the PET? We first need to find O. Plot the wind velocity of 090 at 35 knots on your navigation computer. Rotate the inner scale to put the outbound track of 030 against the 12 o'clock index, and move the speed scale to put 180 knots TAS under the centre circle. You can see that this gives an initial 11 degrees of port drift. You now need to balance the drift in order to get an accurate ground speed. Rotate the scale until the heading reads 040 degrees with 10 degrees of port drift. This gives you a track of 030. This gives O as 160 knots. Now we find H. If the outbound track is 030, the homebound one must be the reciprocal 210 degrees true.
rotate the inner scale to put the homebound track of 210 against the 12 o'clock index, still keeping 180 knots TAS under the centre circle. You can see that this gives an initial 9 degrees of starboard drift. Balancing the drift again, rotate the scale until the heading reads 200 degrees, with 10 degrees of starboard drift. This gives you a track of 210 and gives H as 195 knots. The TAS was 180 knots. Notice that O was 160, giving a 20 knots headwind component. H is 195, giving you a 15-knot tailwind. This becomes obvious when we look at the triangle of velocities. The outbound track is 030. Plot in the wind, 090 at 35, downwind. With a pair of compasses, draw arcs corresponding to 180 knots of TAS, and draw in the lines corresponding to the air vectors. This is O, with its heading of 040, and this is H, with its heading of 200. You can see that the geometry of the triangle of velocities does not always give a tailwind component of the same value as the headwind reversed. You have to solve the triangles with a navigation computer in both directions. If you make approximations of the wind component, using rule of thumb methods, or assume that the tailwind component is the headwind component reversed, you may well get the wrong answer. Let us summarize what we have covered. Point of equal time, or critical point, can be found from the formula x equals d times h over O plus h. This is the starting point for all point of equal time questions. Some calculations assume a constant wind component all along the route. However, the forecast wind may well vary over the flight. This is not a problem, because the equation deals with this situation as long as the wind change point is assumed to be the critical point. Forecast wind along a route can be split into two halves, and then averaged over each half. Emergency situations may also result in a loss of altitude and power, and consequently a reduction in TAS. The same equation also covers this case, as long as the reduced TAS is used in the calculation. However, if a reduced TAS is used to calculate the position of the critical point, the time to the critical point is still based on the all engines ground speed. Unless there is a strong wind component, there is usually little difference between the position of the one engine out critical point and the all engines critical point. In order to keep the decisions simple, we use just one point of equal time. This is always the one engine out case. And finally, if you are given wind velocity and track instead of component, and you have to calculate O and H yourself, you have to solve the triangles with a navigation computer in both directions.
There are occasions when we need to conduct flights to an airport where there are, quite literally, no alternates at all. The most obvious example is an isolated island airport surrounded by ocean with no nearby airfield. The route from Santiago in Chile to Easter Island, a popular tourist destination, is one such example. It is 2,029 nautical miles with no airfield available after crossing the Chilean coast outbound. There are alternates near Santiago shortly after takeoff. Valparaiso is one, for example, but there is absolutely nothing near our destination. In this case, the question is not what is the nearest diversion, but can we safely fly the route at all with the fuel available? We cannot afford to take the risk of arriving at our destination to find that the weather makes a landing unsafe and that we do not have enough fuel left to go back. We are going to establish the maximum range that we can fly outbound and still return within our safe fuel reserves. This limit is called the point of safe return. Let's look at this idea in more detail. Here is a continent or large landmass. Here is our departure airport with a nearby alternate. And here is our island destination. Let's assume that the aircraft has a total endurance to tanks dry of 11 hours. However, we don't operate down to dry tanks. We'll also assume that from the departure airport direct to the alternate requires half an hour's alternate fuel, and that we need to land at the alternate with 30 minutes final reserve fuel. If we go out and back along the route, we must return to the departure airport with a minimum of 1 hour's fuel. We'll disregard contingency fuel in order to keep the explanation simpler. This means that we have a maximum of 10 hours fuel to use on the outbound and homeward flight. Our question is, how far can we go outbound and still return with 10 hours fuel? Shortly before we get to that point, we make a last check on the weather and also confirm that the runway is not blocked. If the answers are unsatisfactory, we turn back. If everything appears in order, we proceed. But we had better be right, because once we pass beyond the point of safe return, we cannot get back with our safe fuel reserves. Let's assume that our aircraft has a true airspeed of 300 knots. In still air, the time and distance to the point of safe return are obvious. It will be 5 hours out and 5 hours back again. At 300 knots, this will be 1500 nautical miles. We do not consider the time taken in the turn to be significant. Turning through 180 degrees at rate 1, 3 degrees a second, takes only 1 minute. This is negligible compared with the total flight time. The still air case was easy, but what if there had been a head or tailwind component, as there usually will be? We can develop a general solution, whatever the wind component, by the use of algebra. We will now derive the formula to calculate point of safe return in general terms. We'll call the safe endurance E. Note that this is the safe endurance. It is the fuel to be used during the flight and does not include reserves. If we include fuel to dry tanks, we would call it the total endurance. The outbound ground speed to the point of safe return is called O. And the return ground speed back to the airfield of departure is called H. The unknown quantity which we are trying to find is the time to turn back, which we call T. Clearly, the distance out must be the same as the distance back. And distance is speed times time. So the outbound distance is the outbound speed times the time it takes to get there. If E is the safe endurance and T is the outbound time, the return time must be E minus T. Therefore, the homebound distance is the speed, h, times the distance, E, minus T. Let's multiply these terms out. OT equals EH minus TH. We'll write OT as TO. But we want to isolate T, so let's get both terms containing T on the same side of the equation. We factorize, then divide both sides by O plus H. This gives our equation for T. T equals EH over O plus H. This is the one you must remember. You will not be examined on the derivation. We showed it to you to demonstrate that this equation is based on good logical algebra and is correct. But whether you remember the derivation or not, you must remember the result. Finally, having got the time to the point of safe return, we get the distance by multiplying T, the time, by O, the outbound ground speed. point of safe return used to be called point of no return, and often still is. You can see why. Up to this point we can return safely, so point of safe return is a good name. But once we pass it, we cannot return. We are committed to going on, so it is also the point of no return. Both names have been used, but possibly point of no return sounds a bit too much like the Bermuda Triangle these days. However, if you see any of the following terms, point of safe return, point of no return, PSR or PNR, they all mean the same thing. However, they are not the same as point of equal time or critical point. Let's remind ourselves of the difference. Point of equal time is a time problem. It is about achieving the shortest time to the nearest alternate. The amount of fuel carried is not a consideration and does not appear in the equation. What is important is the distance between the alternates, and this is an essential entering argument for the calculation. Point of safe return is a fuel problem. The distance between the two airfields makes no difference to the calculation. How far you can go out and come back on a single load of fuel is the same whether the destination is here or here. Clearly, this second situation is much more satisfactory from a practical point of view. It means that you can proceed to the destination, fail to get in, and still get back to the departure airfield. But the distance between the airfields does not affect the calculation of the point of safe return. You can think of point of safe return as a radius of action for a given amount of usable fuel. In fact, the longest route in the world with no destination alternate is Santiago to Easter Island at 5 hours, but the aircraft used, the Boeing 767, has enough fuel to make the journey there and back. The destination is inside the point of safe return. However, that would not be the case for an aircraft with a shorter endurance. Because the formulae for point of safe return and point of equal time are so similar, it is easy to confuse them. However, there are important differences. A point of equal time situation is an emergency, often following an engine failure. The flight may have to be carried out at whatever altitude is safe or can be attained, which may be non-standard for the direction. A point of safe return is not an emergency. It is a regular plan for that route to cover the case of weather being out of limits or the runway being blocked. The procedure may have to be invoked quite often, depending on the frequency of bad weather in the region. Also, the route is flown at normal planned flight levels, including the correct semicircular for the direction. Be sure that, in any exam question, you understand what is being asked. Remember that point of equal time questions often include unnecessary endurance information, and point of safe return questions often include unnecessary distance information. Examiners are like that. Let's now apply the basic point of safe return equation to some numbers and see what the effect of wind is. We'll start with the still air case. We will assume that we have a total endurance of 11 hours, but that we need to keep half an hour for alternate fuel and another half hour for final reserve fuel. Our safe endurance is therefore 10 hours. As before, we'll disregard contingency fuel in order to keep the sum simple. Our true airspeed is 300 knots. Get the basic equation down and then start substituting into it. T equals EH over O plus H. E is 10 hours and H is 300 knots. Put them in. So, 10 times 300 over 600 is 5 hours. This is what logic and common sense tells us must be right for the still air case. 5 hours at 300 knots comes to 1500 nautical miles. Let's now take the case of 50 knots of headwind outbound. As before, our safe endurance is 10 hours and our true airspeed is 300 knots. Our outbound ground speed, O, will therefore be 250 knots. When we turn round and come home, the headwind becomes a tailwind, making h, the homebound ground speed, 350 knots. Here's the basic equation again. T equals EH over O plus H. E is 10 hours and H is 350 knots. And O is 250 knots. 10 times 350 over 600 is 5.833 recurring hours, or, more sensibly, 5 hours and 50 minutes. 250 knots for 5 hours 50 comes to 1458 nautical miles. The effect of a headwind has been to reduce the distance to the point of safe return. What about 50 knots tailwind? As before, our safe endurance is 10 hours and our true airspeed is 300 knots. With 50 knots tailwind, our outbound ground speed, O, will be 350 knots. When we turn round and come home, the tailwind becomes a headwind, making h, the homebound ground speed, 250 knots. Back to the basic equation, T equals EH over O plus H. E is 10 hours and H is 250 knots. And O is 350 knots. You do the calculation this time. Don't click onto the next scene until you've got a result for both T and for the distance to the point of safe return. You should have come up with the answers 4.166 recurring, or 4 hours and 10 minutes, and 1458 nautical miles. So we have shown that the maximum range is always the still air case. Whether the component is head or tail, the effect of wind is always to reduce the distance to the point of safe return. If you increase speed on the outbound leg, you reduce it on the inbound leg and vice versa. However, you always lose more by slowing down than you gain by speeding up by the same amount. Let's summarise this lesson. The maximum range that we can fly outbound and still return within our safe fuel reserves is called the point of safe return. It is dependent on fuel and is not affected by the distance between the departure and destination airports. It can be called point of safe return, point of no return, PSR or PNR. The basic equation to find the time to the PSR is T equals EH over O plus H. Having found the time, the equation to find the distance is distance to the PSR is O times T. Despite the similarity of the formulae used, it is a completely different case from point of equal time or critical point. The maximum range is always the still air case. Whether the component is head or tail, the effect of wind is always to reduce the distance to the point of safe return.
In this lesson, we'll start by checking that we can use the basic point of safe return equation. Here is a typical question. Your total endurance is 7 hours and 40 minutes. Required reserves are 1 hour and 40 minutes. The true airspeed is 200 knots. The distance from departure to destination is 1200 nautical miles. The outbound wind component is 30 knots tail. Assume that the wind remains constant. What is the time and distance to the point of safe return? These are the possible answers. Don't click onto the next scene until you have the answers. Let's go through it,
Your total endurance is 7 hours and 40 minutes. However, the required reserves are 1 hour and 40 minutes. These must be available on arrival back at the departure airfield. This leaves 6 hours safe endurance. The true airspeed is 200 knots. The distance from departure to destination is 1,200 nautical miles. But this is irrelevant to the question. It will make no difference to the point of safe return. The outbound wind component is 30 knots tail. So O will be 200 knots TAS plus 30 knots. This gives a ground speed of 230 knots. We can assume a constant wind. So the wind component on the return part of the flight will be 30 knots head. Therefore H will be 200 knots TAS minus 30 knots. This gives a ground speed of 170 knots. Write down the standard equation T equals EH over O plus H. Substitute your known values for E, O and H, and you should have got 2.55 hours, which is 2 hours and 33 minutes, or 153 minutes. The distance to the point of safe return is O times T. O is 230 knots, and T is 2.55 hours, which comes to 586.5 nautical miles. We'll call that 587 for all practical purposes. So answer A was the right one. These basic equation questions are fairly straightforward. There are only 2 points to watch out for. One is, don't use the point of equal time formula for a point of safe return question, but we have covered that. The other is if you are given a wind velocity instead of a wind component. The geometry of the triangle of velocities does not always give a tailwind component of the same value as the headwind reversed. You have to solve the triangles with a navigation computer in both directions. If you make approximations of the wind component using rule of thumb methods, or assume that the tailwind component is the headwind component reversed, you may well get the wrong answer. All the solutions that we have seen up till now make the assumption that the fuel is used at a constant rate and that endurance is linearly related to fuel contents. This may be unrealistic. This would assume that a fuel graph, or how goes it, as it is often called, takes this form, with a straight line graph of fuel against time or distance. In fact, a practical how goes it usually looks more like this. There is an initial steep slope because the climb is usually carried out at maximum continuous power, whilst once at top of climb, it is normal to set long-range cruise. So the fuel flow rate is higher. In addition, the aircraft is usually climbed at a slower speed than in the cruise, so the distance covered in the time is less. Once at top of climb, the aircraft is heavier than it will be later in the flight when some fuel has been burnt. The fuel flow per nautical mile will therefore be greater. If the aircraft is flown using a constant power setting, the speed will be slower in the early part of the flight, whilst if the aircraft is flown at a constant speed, more power and therefore more fuel will be needed whilst the aircraft is heavy. However, as the weight reduces, the kilograms per nautical mile will increase, and the slope will reduce. There is another reason why the fuel flow may not be constant. Point of safe return procedures are not an emergency, and they will therefore be flown at the correct semicircular flight level to conform to air traffic control regulations. Even if all other factors were equal, we would expect the true airspeed and fuel flows to be different on the outbound and return legs. To cope with this usually more realistic situation, we have another equation. Rather than derive it by algebra, we shall simply quote it. We will then do a worked example, and the way that it works will become obvious. D is the distance to the point of safe return. F is the safe fuel. This is quoted in kilograms or pounds or gallons, or whatever units are used for that aircraft, not in time. As it is the safe fuel, it does not include the reserves. If the reserves were included, it would be called total fuel. CO is the specific ground range outbound. Specific ground range is fuel used per nautical ground mile. CH is the specific ground range homebound. The formula to be used is D equals F over CO plus CH. Now let's see how it is used. Here's the formula again. We'll say that we fly outbound to the point of safe return at flight level 270 and return at flight level 310. F, our safe fuel, is 39,500 kilograms. Our TAS remains constant at 310 knots. We have 30 knots tailwind outbound and 30 knots headwind inbound. The fuel flow outbound at flight level 270 is 6,250 kilograms per hour, and the fuel flow homebound at flight level 310 is 5,300 kilograms per hour. We need to find CO and CH. The first thing to do is calculate O and H. O is 310 knots TAS plus 30 knots tailwind. That's a ground speed of 340 knots. H is 310 knots TAS minus 30 knots headwind, or 280 knots ground speed. CO is fuel flow outbound divided by ground speed outbound. Let's see why. We use 6,250 kilograms per hour outbound, and our ground speed outbound is 340 knots. However, another way of describing ground speed in knots is that it is nautical ground miles per hour. We are dividing by per hour in both the numerator and the denominator, which means that they cancel. The answer is 18.382 kilograms per nautical ground mile. We apply a similar logic to CH. It is 5,300 kilograms per hour homeward, divided by 280 knots ground speed home. Again, the per hours cancel, this time giving us 18.929 kilograms per nautical ground mile. So, CO plus CH, the bottom line of our equation, comes to 18.382 plus 18.929 kilograms per nautical ground mile, which totals 37.31 kilograms per nautical ground mile in both directions. Let's draw in 1 nautical ground mile. Here it is. We use 18.382 kilograms flying out and another 18.929 kilograms flying back.
making a total of 37.31 kilograms there and back. So all we have to do is see how many times we can fit 37.31 kilograms into 39,500 kilograms, which is all of our safe fuel. It comes to just over 1,058 nautical miles. So now that we have the distance, we can find the time from the ground speed outbound. The time will be this distance divided by O, which is 340 knots. Let's summarize this lesson. We revised the basic point of safe return equation, the one you should normally use if the fuel flow can be assumed to be constant. It was T equals EH over O plus H. We also reminded ourselves not to use the point of equal time formula for a point of safe return question, and of the need to use the navigation computer to properly solve the triangle of velocities in both directions if given a wind velocity instead of a component. However, we then found that the basic formula is based on the assumptions that the fuel is used at a constant rate, and that endurance is linearly related to fuel contents. This may be unrealistic, firstly because the fuel consumption changes as the weight reduces, and secondly because the outbound and return legs may be flown at different flight levels. To cover the case of variable fuel flows, we have another equation. D equals F over CO plus CH. And we saw why this works by showing a worked example.
This is the first of 3 lessons on grid navigation. This one explains what it is and why we do it, and then explores the idea of convergence. The later ones will look at steering when using grid and the solution of grid problems. Grid navigation is a technique in which, rather than using the normal latitude and longitude graticule as a reference for direction and positions, we apply a square-shaped grid and use that instead. Why should anyone wish to do this? The reason is that, at high latitudes, the amount of meridian convergence becomes significant and causes problems in defining and steering a direction. Let's take a high latitude situation. We'll suppose that we wish to fly from 70 west, somewhere in Canada, to 70 east, somewhere in Russia. We want to fly the Great Circle track, or as near to it as possible, because it's shorter than the run line. Here is the same situation on a polar stereographic chart. Position A is at 70 west. The line defining true north is the line joining it to the North Pole, that is, the meridian of 70 west. The track from A to B makes an initial track angle of 0 to 0 degrees true at A. So suppose we set off from A using a compass which gives us true north, and keep applying the appropriate drift in order to maintain a track of 0 to 0 degrees true. But as we cross each meridian going eastwards, the direction of true north changes. Relative to the top of the map, that is, the 12 o'clock position on the page, the direction of true north is turning anti-clockwise. This means that our direction of 0 to 0 will also turn anti-clockwise on the map. If we maintain our track of 0 to 0 true, our path over the ground will look something like this. Exactly the same problem occurs at lower latitudes, unless a direct Mercator chart is being used, but is usually not noticed. Suppose that we wish to fly from C to D, which are both at 53 north. The mean track is 090 true. We are using a Lambert's chart. We now have a choice. We could maintain a track of 090 true. If we do, we will still finish up at D, but we will fly the run-line track. If we were to take a succession of fixes whilst flying, but not alter track direction, they would appear like this. However, this is not how most navigation actually takes place. The idea of having a straight line on your chart is that it is supposed to be the track that you are trying to fly. If you wanted to fly the run-line track, you would use a Mercator chart. So most non-automatic navigation is done using the other option. In this, we measure the initial track of 082, and then set off on it and settle into our normal cycle of fixing and correcting back to track. After a while, we take our first fix. There will probably be some cross-track error. This will mainly be caused by changes from the forecast wind and inaccurate flying of headings. This cross-track error will also include a small component caused by holding a track of 082 true, whilst the straight line track has actually altered to, say, 083, but this will be completely swamped by the other random errors. We don't even notice the cross-track position error caused by convergence because it is usually so small at low to medium latitudes. We plot our fix, then use our protractor to make a normal correction to get back to track. We measure the track locally near the fix, thereby automatically correcting for the convergence. During the course of the leg, the datum track will change from 082 to 098 true, but the process happens simply by correcting back to the straight line track on the chart and measuring the local meridian. However, this technique of sweeping the change of track into the normal navigation corrections breaks down at higher latitudes because the amount of convergence becomes too great to ignore. We therefore have to abandon true north as our direction datum and use a grid and its associated grid north on our chart instead. We also have to align our compasses to grid north, not true north, and keep its direction up to date as we fly along the track. But at least now we have a track that can be defined by a constant direction. There are various different methods for selecting the datum direction for grid north, but for the EASA ATPL syllabus, the datum chosen will always be a meridian of longitude. First, we choose a meridian to use as our datum. We add the horizontal parallel lines at suitable intervals, often every 60 nautical miles, but they can be smaller or larger distances. And then we sweep out an arc to draw the vertical lines the same distance from the datum meridian and parallel to it. And then continue to construct the full grid. If the Greenwich meridian is chosen as the datum meridian, we call it a standard grid. Standard grids are widely used on printed grid maps for the European area. Another favourite datum meridian, often used in the USA and Canada, is 60 West. We'll now examine the relationship between true north and grid north and see how it changes over the chart. We'll start with a latitude and longitude graticule. We choose one particular meridian as the datum. It doesn't have to be the Greenwich meridian, but it is in this example. At the datum meridian, grid north and true north are the same. Now, let's consider the grid line that passes through longitude 10 west. Being part of a grid, it is parallel to the datum meridian. But longitude 10 west will be inclined to the datum by the amount of chart convergence between itself and the datum. A line of longitude defines local true north. Therefore, the difference between true north and grid north at any point on the chart is the amount of chart convergence between the longitude being considered and the datum. This is exactly the same chart convergence you learnt about in maps and charts. If the chart is a polar stereographic, the convergence will be the change of longitude. If it is a Lambert's, it will be the change of longitude times the sine of the parallel of origin, or little n. So this gives our definition. Grid convergence is the angular difference between true north and grid north at any particular point on a grid chart. We've just seen that we can work out the magnitude of convergence. We also need to be able to work out its sense. Is it east or west? There is a logical way of doing so, and it depends on whether the point on the chart that we are considering is east or west of the datum, and also whether we are in the northern or southern hemisphere. The vertical centre line represents the datum meridian. This time we have chosen one which is not Greenwich. Now let's put in all the other meridians either side of the datum. And now we add the grid. We'll start by considering a meridian out to the east of the datum. Now let's look at the inclination of the meridian in the southern hemisphere. Everywhere, except at the equator, it is always further clockwise than grid north. At the South Pole, it is 90 degrees out to the east, and at the equator itself, it is parallel. At any latitude in between, true north is east of grid north by some angle between 0 and 90 degrees. Let's now consider the same meridian in the northern hemisphere. You can see that here the red line, which is true north, is always anti-clockwise or west of the green grid north direction. We'll now look at a meridian west of the datum. Up here in the northern hemisphere, the meridian is always clockwise or east of the grid line. And finally, in the southern hemisphere, west of the datum, the meridian is always inclined west of grid north. This gives us the pattern east-west, west-east. It is one of those useful mnemonics like D-I-I-D, which we have encountered earlier in the course. Remember and use it when solving grid problems. Convergence is annotated easterly when true north lies to the east of grid north, and westerly when true north lies to the west of grid north. And it follows this rule: convergence east, true least; convergence west, true best. This shows convergence east, true least. True north is out to the east of grid north. So convergence is defined as east. The grid heading is 105 degrees. Convergence east, true least. True should be 20 degrees less than grid. So the true heading should be 085, which it is, as we can see. This one shows convergence west, true best. True north is out to the west of grid north. So convergence is defined as west. The grid heading is 105 degrees. Convergence west, true best. True should be 20 degrees more than grid. So the true heading should be 125 true. Convergence follows the same pattern of conversion of direction as our previous conversions of true variation magnetic deviation compass. But note that it goes on the left-hand side of the columns if going from true to compass. So, to give an example, if the grid heading is 090 and the convergence is 10 west, then true will be 100. The rest fills in the familiar way. And, as you would expect, we follow the same rules when working from compass to true to grid. If the true heading is 100 and the convergence is 10 west, convergence west, true best, then grid must be 10 degrees less than true, giving us a grid heading of 090. Now that we can convert from true to grid on the chart, we need to find a method of steering grid direction. This can be done using either a compass or a gyro, as we shall see in the next lesson. Let's summarize this lesson. It is the first of 3 lessons on grid navigation. It explains what it is and why we do it, and then explores the idea of convergence. The later ones will look at steering when using grid and the solution of grid problems. Grid navigation is used because, at high latitude, the amount of meridian convergence becomes significant and causes problems in defining and steering a direction. We use a grid and its associated grid north on our chart instead of latitude and longitude. And we also have to reorientate our compass or gyro. But we are able to define a constant direction for our straight line track. We choose one particular meridian as the datum. And from this we define our grid. We showed that our normal definition of chart convergence is also the difference between true and grid north at any point on the chart. So we can calculate the convergence by taking the change of longitude between the datum and any particular longitude on the chart and applying the normal rules, depending on whether it is a polar stereographic or Lambert's chart. Remember the rule EWWE to work out whether the sense of the convergence is east or west. Remember that convergence is east when true north lies to the east of grid north, and west when true north lies to the west of grid north. And remember, convergence east, true least, convergence west, true best. And finally, we showed that converting from grid to true follows the same simple rules as converting from true to compass, but note that the grid and convergence columns go on the left, if we are going left to right from true to compass. That concludes this lesson. We will study steering by compass or gyro when using grid next. This is the second of 3 lessons on grid navigation. In this one, we examine the problems of providing a source of grid heading. The modern flight management system is usually polar programmed and can continue to operate in true up to very high latitudes, and, in any case, is not so concerned about chart convergence, as no chart plotting is required in order to provide the required steering signal. However, if grid flying is carried out in an aircraft without FMS, the source of heading is either a gyromagnetic compass or a high-grade gyro. We are going to see how we obtain grid, as opposed to true or magnetic, heading from whichever of these 2 sources we are using. If grid technique is being used because of the problem of meridian convergence at high latitudes, then the aircraft may also be near to one of the Earth's magnetic poles. If so, it may not be practicable to use a magnetic compass because variation may be changing too rapidly or the horizontal magnetic field strength may be too weak. However, even at high latitudes, this may not always be the case. Flying in parts of northern Canada would probably give a problem. But flying in northern Europe or Russia probably would not, because these areas are a greater distance from the North Magnetic Pole. So it may be possible, under some circumstances, to steer by magnetic compass even when using grid technique. The problem is not too complicated and is very similar to the problem of steering true heading when using a magnetic compass. When using true steering, we apply variation to convert the required true heading to magnetic heading, then apply the deviation to get compass heading to fly. For grid steering, all we have to do is apply a combination of convergence and variation to convert the required grid heading to magnetic heading. Finally, we apply the deviation to get compass heading to fly. Here is just the correction from grid to magnetic. The difference between magnetic and grid heading is called grivation, and it is the algebraic sum of variation and convergence. By using grivation, we can go straight from grid to magnetic. We don't need to bother with true as an intermediary step. By the term algebraic sum, we mean that if the signs of variation and convergence are the same, we add them. If they are different, we take the difference. For instance, a convergence of 10 west and a variation of 5 west gives us a grivation of 15 west. However, if the convergence were 10 west and the variation were 18 east, the grivation is 8 east. Printed grid charts have the grivation pre-calculated by the publisher and printed on the chart. Lines on a chart joining places of equal grivation are called isogrids. For some practice at the relationship between convergence, variation and grivation, look at this situation. A straight line track is drawn between 2 points on a Lambert's or polar stereographic chart. The data meridian is C. Now complete the attached table. Your first reaction may be, well, how do I even get started? The trick to remember is that the grid track does not change direction. If you have found the grid track at one longitude, it must be the same grid track at all longitudes. Use your mouse to move the numbers below into the correct box. If you're right, they'll stay there. If not, they won't go in. When you're finished, click to continue. Here are the answers. Now let us see how we would use a magnetic compass to steer a true heading as the variation changes, and then we will see that much the same principles can be applied to steering a grid heading. This short triangular navigation exercise, which is typical of a PPL training route, all takes place between two isogonals. We use 3 degrees variation for the whole route. However, this route from Norwich to Swansea crosses 2 isogonals. Assume that we need to fly a mean track of 254 true all the way along the route. We start off with a variation of 2 west. We will need a magnetic track of 256. But as we cross the 2.5 degree isogonal, our variation changes to 3 west. We must now alter heading to give a magnetic track of 257. Similarly, as we cross the 3.5 degree isogonal, the variation becomes 4 west. Another alteration of magnetic track, this time to 258, is required to maintain a track of 254. If a chart is constructed with isogrids, then the same principles can be used to maintain a grid heading when using a magnetic compass. On this chart, the blue graticule is the latitude and longitude. If you use true heading, then here are the variation changeover points. The grey graticule is the grid. If you use grid heading, then here are the grivation changeover points. You can see that the rate at which the isogrids are changing is much the same as the rate at which the isogonals are changing, so it is no more difficult, in many parts of the world, to fly a grid heading using a magnetic compass than it is to fly a true heading. However, one of the reasons that we may be using grid is because the aircraft is at high latitudes. In this case, a magnetic compass may be unusable in some parts of the world because the route is within the 6 microtesla zone and the horizontal component of the Earth's magnetic field is too weak. In other parts, the rate of variation may be changing too rapidly to be usable. In these cases, we would steer by gyro. The errors of a gyro are real drift, also known as random wander, earth rate, and transport wander. Real drift in INS quality gyros is of the order of 1/100th of a degree per hour. However, if an INS were fitted, it would not normally be necessary to use grid, because most inertial navigation systems are polar programmed and can continue to operate in true up to very high latitudes. Nevertheless, if no INS is fitted, on a typical modern airline quality gyromagnetic compass, the gyro drift rate will still only be about 1/10th of a degree per hour when operating in DG mode. In this case, real drift is low enough to be insignificant. Earth rate occurs because the gyro is aligned with true north at some particular meridian. The aircraft then rotates with the Earth along with the meridian, but the gyro continues to remain in alignment with the point in space where it was originally aligned. The correction factor is 15 times the sine of the latitude in degrees per hour. Many modern gyro compasses have a latitude correction control, which is a knob turned by the crew to be set to the local latitude, and the correction is then fed to the gyro. The crew then keep resetting the latitude as it changes. Transport wander is another name for meridian convergence. The gyro is aligned with true north at some particular meridian. Then, as the aircraft travels either east or west, the gyro remains aligned to the original direction in space, but the direction of the meridians, and therefore the local direction of true north, changes. To operate in true, a correction has to be calculated for this meridian convergence. The correction factor is change of longitude times sine mean latitude. However, to operate in grid, no correction is required. What is required is a direction that does not change with change of longitude, in other words, a grid. Therefore, we use the gyro, but without any correction for transport wander or meridian convergence. It is actually easier when using a gyro to fly in grid rather than true, because you don't have to correct for transport wander. There is, in fact, a small error caused by the difference between Earth convergence, which is the gyro correction, and chart convergence, which will depend on the projection and the standard parallels being used. A correction has to be applied, known as residual transport wander. This is fed in either by slewing the gyro or as a false correction to the latitude control, but its use is beyond the scope of this course and is not discussed further. Therefore, to operate with a gyro in grid, all that is needed is to align it to grid north initially, then feed in a correction for Earth rate. Real drift will be small with a good gyro, and transport wander will be non-existent, or there may be a small amount of residual transport wander to be corrected. Let's summarize this lesson. It is easy enough to produce a grid by drawing parallel straight lines on a chart. This solves the problem of a constantly changing track direction caused by convergence at high latitudes. However, this solves only half the problem. We still need to convert the heading source, whether compass or pure gyro, to the grid direction. It is perfectly possible to fly by compass even at high latitudes, as long as the aircraft is not too close to the magnetic pole. In this case, we use grivation, which is the difference between magnetic and grid north instead of variation, which is the difference between magnetic and true north. Grivation is the algebraic sum of convergence and variation. Make sure that you can convert between grid, true and magnetic directions using grivation, convergence and variation, and understand how they are linked. When the compass is unusable because the Earth's magnetic field is too weak or the variation is changing too rapidly, we may choose to steer by gyro. In this case, the three sources of error are real drift, Earth rate, and transport wander. Real drift is low in modern gyros and can be regarded as not significant. Earth rate can be mechanically compensated by the use of automatic devices. And transport wander, which is another name for meridian convergence, is eliminated or nearly eliminated by the use of a grid. That completes this second lesson on grid navigation. The next one will look at typical grid exam problems. This is the third of 3 lessons on grid navigation. We will start by reminding ourselves about grid convergence, and then go on to the solution of grid problems. A gridded chart is invariably used in polar regions. In both the north and south polar areas, the common plotting charts are polar stereographics or transverse or oblique Mercator's. On all of these charts, the 360 degrees of longitude on Earth are represented by 360 degrees on the chart. This property makes these charts ideally suited for the use of a standard polar grid, which can be printed on the charts for all users. The Greenwich meridian is usually used as the datum meridian. This is a polar stereographic chart, and the grid track from A to B is 090 degrees. We're going to work out the relationship between true and grid track at various points. In order to do that, we'll need to use the east, west, west, east rule. Position A is at 70 west. As the datum is Greenwich, this is west of the datum, in the northern hemisphere. This is easterly convergence. Convergence east, true least. The true track will be smaller than grid by 70 degrees. 090 grid minus 70 degrees gives us a true track of 020. We now continue a long track until we reach longitude 45 west. Again, we are west of the datum. Convergence east, true least. The true track will be 45 degrees less than the grid. 090 grid minus 45 degrees gives us a true track of 045. As we pass the datum meridian, the true and grid tracks are the same. As we get to 45 east, we are now east of the datum in the northern hemisphere. Therefore, convergence is west. Convergence west, true best. The true track will be 45 degrees more than the grid. 090 grid plus 45 degrees gives us a true track of 135. And finally, we'll arrive at B, which is longitude 70 east. Again, we are at east of the datum in the northern hemisphere, so convergence is west. Convergence west, true best. The true track will be 70 degrees more than the grid. 090 grid plus 70 degrees gives us a true track of 160. This all ties in with what you learnt about polar stereographic charts. The longitude has changed from 70 west to 70 east, which is a difference of 140 degrees. Therefore, the true track of any straight line must also change by 140 degrees. In this example, we have gone from 020 degrees true to 160 degrees true. The grid track, however, does not change. Here we have a north polar stereographic projection. Therefore, the n factor is 1, and the chart convergence between any two meridians is simply equivalent to the change of longitude. We are going to work out the relationship between grid and true for each aircraft. Firstly, by inspection of the diagram and common sense, and then secondly, by use of the rules on convergence. Let's first make a point which will help you when you come to draw your own diagrams. It usually helps your thoughts to have grid north at the top of the page. In the northern hemisphere, this means having the datum meridian at the 6 o'clock position, because north is the direction that runs into the North Pole. Let's start by looking at aircraft number 1. Just by inspection of the diagram, you can see its grid heading is 360 grid, whilst the true heading is 270 true. Therefore, the true heading is 90 degrees less than the grid by simple visual inspection. Now work it out using convergence. If grid north is at the 12 o'clock position, then the datum meridian must be the Greenwich meridian. In other words, this is a standard grid. Aircraft 1 is at longitude 090 west, which means that the aircraft is west of the datum. If we're west of the datum in the northern hemisphere, convergence is east. Convergence east, true least. Therefore, true heading should be 90 degrees less than the grid, which it is. Both the convergence formula and the diagram give the same answer. Now try the same exercise for aircraft numbers 2 to 5. Do it both ways, firstly by visual inspection and then secondly by using the rules. Get a piece of paper and work out what goes in each of the blanks. When you're finished, click to continue to check your answers. Here are the answers. Now let's do it for the southern hemisphere. This is slightly more of a brain stretcher. To get grid north at the top of the page in the southern hemisphere, we need the datum meridian at the 12 o'clock position. In the southern hemisphere, north is the direction that runs out of the South Pole. You know what to do now. Just remember that convergence east and west are the other way round in the southern hemisphere. It's actually easier because you don't change the sign. Now try the same exercise in the southern hemisphere. Again, do it both ways, firstly by visual inspection and then secondly by using the rules. Get a piece of paper and work out what goes in each of the blanks. When you're finished, click to continue to check your answers. Here are the answers. Now we'll try some problems of the sort that you might meet in an exam. In these kinds of problem, there are 4 factors. These are the datum longitude, the aircraft longitude, grid track, true track. The question will normally give you 3 of them and you have to find the 4th. This one is for a polar stereographic chart. The aircraft position is 45 north, 110 west. The grid track is 132. The datum is at 60 west. What is the true track? We'll start by working it out using the rules. Is the aircraft east or west of the datum meridian? The aircraft is at 110 west. The datum is 60 west. The aircraft is therefore 50 degrees west of the datum. Is that east or west convergence? We're in the northern hemisphere. It must be easterly convergence. With a polar stereographic chart, little n is 1. 50 degrees of change of longitude is 50 degrees of convergence. So, the convergence is 50 east. Convergence east, true least. So what is the true track? A grid track of 132 minus 50 gives a true track of 082. We recommend that you simply apply the rules as we have just shown. However, we will give you the diagram solution as well, so you can envisage the situation. Firstly, plot the aircraft position of 45 north, 110 west. We are looking down on the Earth from above the North Pole. This is 110 west. Try to estimate the longitude reasonably accurately. The latitude doesn't matter on these diagrams. There is no latitude scale anyway. Draw in the datum meridian. This gives you the direction of grid north. Parallel grid north so that it passes through the aircraft position. draw in a track of 132 grid. Now compare your grid track with your true north direction. You can see that it is about 082. With a diagram like this, you would be able to work out the correct solution from the given multiple choice answers. This one is similar. As before, you are given 3 of the factors and you have to find the 4th. Again, we are using a polar stereographic chart. The aircraft position is at 28 south, 118 east. The true track is 042 and the grid track is 133. What is the datum meridian? What is the convergence? Grid track is 133. True track is 042. That's a difference of 91 degrees. True is least, so the convergence is 91 east. Is the aircraft east or west of the datum? We're in the southern hemisphere. With easterly convergence, the aircraft must be east of the datum. If the aircraft is 91 degrees east of the datum, and the aircraft is at longitude 118 degrees east, where is the datum? The datum longitude is 027 east. Again, we recommend that you apply the rules, as just shown. It's usually simpler. However, here is the diagram. The aircraft is at 118 east. True north is the direction away from the South Pole. Plot a track of 042 true from the aircraft. The grid track is 133. This gives you the direction of the grid. Parallel the grid through the South Pole. This gives you the datum meridian. Now we'll do one using a Lambert's chart. The only difference to remember is that chart convergence is no longer simply change of longitude between the aircraft and the datum. You have to multiply the change of longitude by the sign of the parallel of origin of the chart. The aircraft position is 50 south, 178 east. The parallel of origin is 56 south, and its sign is 0.82. The grid track is 192 and the true track is 211. What is the datum meridian? So, we need to find the change of longitude between the aircraft position, which we know, and the datum, which we don't. So, the first question is, what is the convergence? It's the difference between grid and true track. In this case, it is 19 degrees, and it must be west, because true is the bigger number. What change of longitude does this represent? The change of longitude, multiplied by 0.82, gives us 19 degrees. Divide 19 by 0.82 to get 23 degrees longitude change. Which way? Back to the usual diagram. The convergence is west, so the aircraft must be west of the datum. This means that the datum is east of the aircraft. The aircraft meridian is 178 east. The datum must be another 23 degrees east. This comes to longitude 201 east. Take it away from 360 to get 159 west. Here's the diagram solution. Again, you'll probably find applying the rules easier. Plot the aircraft position at 50 south, 178 east. This gives us true north. Draw a true track of 211. The grid track is 192, so we can plot grid north. And you can either parallel the dotted line to get the datum, or use the fact that there are 23 degrees of longitude between the aircraft and the datum. Some questions may provide you with a grid chart as an annex. In this case, you may be expected to solve them by plotting, not calculation. Here is an example. Assume a North Polar stereographic chart whose grid is aligned with the Greenwich meridian. An aircraft then flies from the North Geographic Pole for a distance of 480 nautical miles along the 110 degrees east meridian, then follows a grid track of 154 degrees for a distance of 300 nautical miles. What is the aircraft's final position? The possible answers were 78:45 north, 87 east, 80 north, 80 east, 79:15 north, 74 east, and 70:15 north, 80 east. This one is most easily solved simply by drawing it out. Any calculation would be complicated and time-consuming. Using the scale given on the chart, first draw a line 480 nautical miles long out from the North Pole along the 110 east meridian. Using a protractor against grid north, plot in a track of 154 for a distance of 300 nautical miles. Then, by inspection of the four answers, only one could possibly be correct. All that the examiner is trying to establish is that you realise that grid north is the same direction all over the chart. Let's summarise this lesson. It is the third of 3 lessons on grid navigation. We started by reminding ourselves about convergence. We looked at a polar grid chart and a route which involved a large change of longitude in a short distance. As we travelled along the track, the true track changed from 020 to 160. But the grid track remained 090. At every stage, the difference was the amount of convergence, which was directly related to the change of longitude between the aircraft and the datum. We did a practical exercise on relating aircraft longitude and datum to convergence, true and grid, and we noted that in the northern hemisphere it is helpful to draw the datum meridian at the 6 o'clock position, because north is the direction that runs into the North Pole. However, in the southern hemisphere we need the datum meridian at the 12 o'clock position, because north is the direction that runs out of the South Pole. We then looked at typical exam questions. In most of them, there are 4 factors: the datum longitude, the aircraft longitude, the grid track, and the true track. The question will normally give you 3 of them, and you have to find the 4th. The best way to solve most of these is simply to apply the rules. Don't forget that, if it's a Lambert's chart, you have to apply the sign of the parallel of origin to obtain the convergence from the change of longitude. A diagram may help you to visualize the situation and aid your understanding. Some problems require a graphical solution. And remember, always, that a straight line track cannot change grid direction. This concludes the lessons on grid navigation. Whilst many modern airliners with flight management systems can cope with polar routes without the need for a grid, it is still necessary in older aircraft for high latitude flying.
This lesson is on navigation plotting. So far in your studies, you have become aware of 2 methods of navigation. One is solo pilot VFR navigation, based on the 1 in 60 rule. The other is the use of automatic computing systems, such as INS, IRS, FMS, GPS, and RNAV. However, there is a whole group of aircraft which are more sophisticated than light training aircraft, but less sophisticated than the full jet airliner glass cockpit standard. These aircraft are routinely fitted with VOR, DME, ADF, and gyromagnetic compasses. For this sort of intermediate complexity aircraft, it becomes necessary to plot on a radio navigation chart, or a specialist plotting chart, usually a Mercator's chart or a Lambert's conical orthomorphic chart. The EASA ATPL requirement is for the use of the Lambert's conical orthomorphic, and occasionally the polar stereographic. The chart used for most of the question settings is the Jeppesen ELO1. Any charts used in the exam will be supplied as an annex to the question paper. If plotting is required on any other charts, appropriate annexes will be attached. These are usually skeleton charts or small-scale Jeppesen charts. You will need the following equipment: a navigational straight edge, a square plotting protractor, dividers for measuring, a pair of compasses for drawing DME range arcs, 2 H and HB pencils for plotting, and a soft eraser. The task required is usually not difficult. It may involve, for instance, plotting a VOR DME crosscut, or possibly 2 VOR radials. Sometimes the question is asked in reverse. You are given a position in latitude and longitude and asked to select the correct 2 radials. You will need to know your basic cartographic symbols. You will become familiar with these and other types of question as you try the practice questions associated with this lesson. However, although it is usually easy to understand what is wanted, sometimes the difference between a right and wrong answer is only 2 degrees. It is essential to plot accurately. Bearings can be split into subcategories: relative, or with respect to north, true or magnetic, measured at the aircraft, or measured at a ground station. Each of these considerations affects how we plot them. We'll start by considering relative bearings. There are 2 instruments that may be used for displaying bearing in the aircraft. These are the well-known radial magnetic indicator, or RMI, and the older relative bearing indicator, or RBI. The RMI has a rotating compass backplate, which is driven from the gyromagnetic compass or directional gyro indicator. If correctly synchronized, it continuously shows the aircraft's magnetic heading. In front of this rotating compass indication, there are VOR or ADF needles, or both, depending on the aircraft's navigation fit. We will assume 1 VOR pointer and 1 ADF pointer. The magnetic direction to the navigation aid is read directly off the pointed end of the needle against the compass backplate. Therefore, in this example, the magnetic direction to the VOR is 270, and the magnetic direction to the NDB is 000. Alternatively, you can use the tail end of the needle to obtain the magnetic direction from the navigation aid. In this case, the magnetic direction from the VOR is 090, and from the NDB it is 180. By contrast, the relative bearing indicator, or RBI, has a fixed backplate, which always shows 0 at the 12 o'clock position. It can display only ADF bearings. The 0 represents the longitudinal axis, or heading of the aircraft. The bearing is given as an angle measured from 0 to 359 degrees clockwise. This is called the relative bearing. In this example, the relative bearing is 030. We'll assume that the aircraft is on a heading of 045 degrees magnetic. The relative bearing of the NDB is 030. You can see that this gives us a magnetic bearing to the NDB of 075. This gives us the method of converting a relative bearing into a magnetic bearing. You add the relative bearing to the magnetic heading. If the answer comes to more than 360 degrees, you subtract 360. In this example, we have a magnetic heading of 315 degrees. The relative bearing is 130 degrees. Adding them together gives 445 degrees. We subtract 360 to give a magnetic bearing of 085 degrees. The RBI and the pointed end of the RMI needles give QDM. This is the magnetic track to the VOR or NDB. This is useful for homing to a facility, but not for plotting. We have to measure bearings from the navigation aid, not the aircraft, because it is the VOR or NDB which is printed on the chart, not the aircraft position. We therefore need the bearing from the VOR or NDB. If the information is presented as a QDM, we must convert it to a QDR. As these examples show, this is simply achieved by adding or subtracting 180 degrees. The only raw information which comes in the form of true bearing is the QTE, which is a VDF response to a pilot's transmission. As this is a true bearing from the ground station, it can be plotted directly. All others are in the form of a QDM or a QDR. As we have already said, your first task is to convert any QDM into a QDR. We now have a magnetic bearing from the navigation aid. There are 4 possible ways to plot it. You could align the protractor with a magnetic north arrow, if there is one. The problem is that these tend to be very short, usually just over 1 centimetre, and it is difficult to align the protractor accurately. Remember, we said that accuracy was important. A better method is to find the variation from the isogonals. Then use your protractor to plot the variation at the VOR using the nearest meridian as true north. You now have a magnetic north arrow, but a much more accurate one. You can plot the magnetic radial directly without needing to apply variation arithmetically. In this example, a magnetic radial of 108 degrees is shown. However, if the VOR is on an airway, or better still, is positioned on several intersecting airways, then the airway centre lines will be defined by printed radials on the chart. Take, for instance, Shannon. There are radials of 052 magnetic, 071 magnetic, 080 magnetic, 115 magnetic, and 173 magnetic. Put the centre of your protractor over the VOR symbol and then turn it until the 052 on its scale goes through the 052 radial. The 071 goes through the 071 radial, and so on. You have now aligned the protractor with the same magnetic north that Jeppesen have used, and you can now plot a magnetic radial directly. Alternatively, you can convert the magnetic radial to a true bearing by applying variation arithmetically, and then plot by lining up the protractor grid lines with the nearest meridian. In this example, with a variation of 8 degrees west, a magnetic bearing of 108 becomes a true bearing of 100. Finally, we need to look at whether the bearing was measured at the aircraft or at the ground station. This will not affect situations involving the Jeppesen ELO 1, because the amount of convergence is insignificant. However, if using a smaller scale chart, it may affect bearings which involve a large change of longitude. We have already covered the theory in the lesson on Lambert's chart plotting. If you feel that you need to refresh yourself in more detail on the subject, go back and look at this lesson again. Briefly, VDF and VOR are measured at the ground station. With these, we simply put our protractor over the ground station and plot the bearing. The line represents the correct radio path. However, ADF and AWR are measured at the aircraft position, using the local direction of true north. That is to say, directly up the meridian which the aircraft is on. In this example, it is 060 true. We will then need to add 180 degrees to get a bearing of 240 degrees to plot from the ground station. But we will be putting our protractor down at the ground station position. The ground station's meridian is not parallel to the aircraft's meridian. If we simply plot the reciprocal from the local true meridian at the NDB, the bearing will be in error by the amount of chart convergence between the two positions. We could calculate the convergence between the two meridians and add it to our angle to plot. But in practice, it is much simpler to draw a parallel construction line, which we call the false meridian, and plot the simple reciprocal from that. This is the method that is actually used in practice if the chart convergence is large enough to make the correction worth applying. Normally, we would not apply it to convergences of 1 degree or less. Let's summarize this lesson. The chart used for most of the question settings is the Jeppesen ELO 1. Any charts used in the exam will be supplied as an annex to the question paper. If plotting is required on any other charts, appropriate annexes will be attached. These are usually skeleton charts or small-scale Jeppesen charts. The tasks are generally not difficult, but accuracy is required. You need to know your basic cartographic symbols. Bearings can be relative, or, with respect to north, true or magnetic, and measured at the aircraft or measured at a ground station. We looked at the difference between a radial magnetic indicator and a relative bearing indicator, and saw that you convert a relative bearing into a magnetic bearing by adding magnetic heading. We looked at how bearings can be plotted in magnetic or converted to true. And for those cases where the convergence between aircraft and NDB or radar response is large enough, we reminded ourselves about the false meridian technique. However, the best method of becoming familiar with plotting techniques is to try some practical examples. So you should now work through the questions associated with this lesson. You will need a Jeppesen ELO 1 and your plotting equipment. This concludes this lesson.